Radek, the stage is yours.
Hello, welcome to day 2 of XDC 2020 Developers Conference. We hopefully resolved all the technical issues. We have even prepared some neat animation for the case when issues that we didn't predict will happen again. So hope you liked it. I think I'm audible, so microphone works. Cathedral effect is no longer here. Turns out that we did fry a switch yesterday, but we already have a new one. And also we are prepared for heavy storms and power cuts. So we should be able to continue this smooth experience brought to you. So jumping to the thank you notes for our sponsors and organizers now. So conference is brought to you by Intel with X.Org Foundation. So thanks a lot for organizing it. Platinum sponsor for this year's conference is Intel. Thank you, Intel, for your support. Gold sponsor number 1 is Google. Thank you, Google, for supporting XDC this year. On the same level of sponsorship, gold level sponsor NVIDIA. Thanks a lot for being with us this year as well. We have a bunch of silver sponsors. Thank you, Collabora, for supporting XDC on silver level. Thank you, Igalia, for being silver sponsor for XDC 2020. Big thanks to the Linux Foundation for sponsoring XDC this year on silver level as well. Thank you for silver level sponsorship to Microsoft. Thanks AMD for sponsoring XDC on silver level. Thanks ARM for doing the same. We really appreciate all the support we received this year. Thanks goes to all the bronze sponsors we have, to the Kronos Group, thanks a lot, to the Dorota Chaplejewicz, and to GitLab. Thanks a lot for sponsoring the XDC 2020. Big thanks also goes to all our supporters. Thank you, Codeweavers, for supporting XDC this year. And thanks to LWNet for supporting website hosting. Good. Let's start with some logistic updates for the day 2 of this year's conference. So just a reminder, all the links for live streams, all the useful information, links to attendee guides are on our XDC 2020 webpage. Make sure you check it out for all the news about what is currently happening, links. Please follow us on Twitter as well. If you have any questions related to the logistics, don't hesitate and reach out to the organizing team on IRC on Freenode. I actually have mistake here. It's XDC not with capital letters, but hopefully all the folks already are aware of it. So nicknames are listed here. We are all available on the IRC channel, both XDC 2020, the presenters channel, and also questions and answers. One reminder, I think we didn't highlight this opportunity for folks to interact on XDC good enough or well enough. So there is possibility for anyone interested to set up hallway discussion on Jitsi. We've set up Jitsi instance for you to use. So feel free to set up dedicated rooms and inform folks that would like to discuss specific topic related to the conference. Make sure that you made this information available on the XDC. You share on XDC IRC channel. You really share the link. So, the more the merrier when it comes to people joining various talks. The program, again, up to date, available on our web page. Please make sure that you check out the workshop section today, because there is workshop happening in parallel to some other talks. There is a live stream for workshop as well, and it will be available after the workshop happened for you to take a look after the day 2 of the conference. We are still capturing a proposal for lightning talks and demos for Friday. We'll add this to the agenda on first come first served basis. Make sure that all hallway track topics and workshops, if there is something to present and share with wider audience, you notify us, and we'll be able to add this to the agenda on Friday. As small reminder, again, we have this beautiful orange color in the agenda. It's describing basically the workshop track. Make sure that if you are interested in buffer constraints, you join it today. If you would like to set up one another workshop, please let us know, and we'll work on helping you out with this. Just a reminder, we are dedicated, and X.Org Foundation is dedicated to provide you a harassment-free experience. We do not tolerate any harassment to any participants in any form. Make sure you do report any code of conduct breaches. You can do it by sending email directly to myself or Paul, and also you can message us organizers on IRC as well. And last but not least, we really appreciate feedback. I hope you enjoyed day 1, and I hope you are excited and looking forward to the day 2. We have really good lineup of interesting presentations coming soon. So make sure that you drop us a note if you think there is something we could improve. Along the way, you will see that we have already multiple improvements in place. We learn every day, as this is our first virtual conference, and we hope to continue bringing you this great experience and opportunity to interact with experts in the area of open source graphics. Thanks everyone for listening. Have a good day 2 experience, and see you around. Thanks.
Yeah, thank you very much. And next talk will be a year of ACO from prototype to default in about 10 minutes.
Hey there, my name is Timur Kristóf. I'm a contractor for Valve, and I came here to talk to you guys about ACO, short for AMD compiler. I'm going to tell you a little bit about our story. I will recap how ACO works. And after that, I'm going to discuss what kind of changes we needed to do to ACO before we could make it the default shader compiler in Radv. And finally, I'll give you some hints about our plans for the future. So for me personally, the journey began sometime last year when I started to contribute to Mesa as a hobby. And shortly after, there was a guy on IRC who popped up and asked me, this is all good, and would you like to do this for us now? And at first I thought that this was a prank because, surely it can't be true, but it was too cool to say no. So I said, yes, of course, why wouldn't I? And that's how I joined the team at Valve. So we are contractors, and at the same time, there was a guy named Daniel who started working on a new compiler backend for AMD GPUs. And shortly after I joined, I was given the opportunity to join ACO. And I thought, why not? It's a very cool thing. Let's see what happens, and let's see where this road takes us. Our motivation for developing ACO is primarily to give gamers a fluid, stutter-free experience. This means that when you start your game, you have to sit less time in front of a loading screen. For native Vulkan games, it's basically just about the loading screen, but since this is Linux gaming, we also have a thing called DXVK. And the thing about DXVK is that it compiles a lot of shaders, probably more. So there are some games, you start it and you start playing, and it just never stops compiling shaders. It will compile them all the time, all day, every day. So we prioritize compilation speed. The other advantage is that ACO is developed as part of Mesa. So if there are any issues, and there sometimes are, those can be fixed within the boundaries of Mesa releases, independently of the schedule of any other project. And since we started with a clean slate, we can also utilize some new compiler advancements in order to better optimize runtime performance. ACO was presented to you guys at the last XDC. So here's just a quick reminder of where we were at the time. So at XDC 2019, originally ACO supported pixel shaders only. And I think just shortly before XDC, we added support for compute and vertex shaders. And basically that was it. We didn't have any other things, anything juicy. And I think Daniel started working on ACO using the Polaris GPU. So that's what originally was supported. And shortly after that, I think around the end of 2018, maybe support for Vega was added. So what have we been doing since then? I prepared a couple of numbers for you guys. Shortly after XDC 2019, ACO was merged in Mesa. And since then, we've had more than 300 merge requests. We now have 5 contributors. We now support 15 shader stages instead of the first 3. And we support every GCN and RDNA GPU that is currently on the market. And besides that, we also reached full feature parity with the old backend in Radv, which means that whatever you could do with redv without ACO, you can also do that, and maybe a little more when you use ACO. So we also reached full conformance with the spec on your hardware. Sadly, I didn't bring you guys any benchmarks this time, but I can recommend to take a look at Phoronix, which is a great site and has lots of awesome benchmarks about ACO, among other things. And our compile time is pretty consistent with what we had last year, so I didn't think it's worth to go into that too much. Where does ACO fit into the graphics stack? So if you run a Vulkan application, for instance, your favorite game, the game will have the shaders in the SPIR-V format. So we have to parse the SPIR-V into the so-called NUR, which is the intermediate representation used by Mesa. And this takes care of any kind of syntactic or semantic analysis. And once it is parsed, we perform some lowering and optimizations, which means that we get the shader ready for consumption by redv and ACO. And finally, this is what I'm going to talk about today, is the shader compilation with ACO, which means that from the SPIR-V program, you get an actual binary that your GPU hardware can execute. So how does ACO work? And for those of you that didn't visit XDC last year, I'd like to do a quick recap on that. So we start out with just the NUR shader. And from there, we iterate over every instruction in the shader, and we decide what kind of ACO IR instruction fits best. ACO IR is our own intermediate language. It's pretty close to the actual hardware assembly. So it's almost GCN or RDNA instructions. But one thing that's very important about it is that it's SSA all the way. So once we decide what instructions to use, we do value numbering and optimizations. A couple of these are, for instance, common subexpression elimination, constant propagation, and we are also able to combine multiple simpler instructions into fewer but more complicated ones. For instance, we can combine multiplications and additions into the MAD instructions, and so on and so forth. After this, we have to take some steps to ensure that reductions work. And the AMD hardware has this specific, which is called the exec mask, which controls which SIMD lanes are active at any given time. So we need to insert some special instructions to ensure that whatever we want to happen happens on whatever SIMD lanes we want it to happen on. After this is done, we perform a live variable analysis. This can calculate the register need. So this is contrary to other compilers where the register usage really can only be calculated at later stages. But thanks to our using SSA, we can already do it here. And this will be used for spilling and scheduling. So our spiller, what it does, first it lowers the shader into the so-called CSSA form, or in other words, conventional SSA form, which is required because there are certain guarantees that we need. So one thing that we need is that we need to ensure that we wouldn't need any memory-to-memory moves. And CSSA gives us that guarantee. So after transforming it to CSSA, the spiller works until it decreases the register usage to an acceptable level. And after this comes our instruction scheduler. So here, again, we use a relatively new and interesting approach. So other instruction schedulers usually take the entire program and try to build up a whole new schedule from scratch. In contrast, what ACO does is that it basically just uses the original structure of the program, but it tries to find more important instructions, which it will try to move up as high as possible. One prime example of this are load instructions. So if it moves the loads up, that means that whatever it loads will be available to the rest of the shader as soon as possible. After this, we do our register allocation, which works on the aforementioned SSA-based IR. And it then emits some shuffle code, which means that some temporaries actually don't just need a single register, but a vector of consecutive registers. So when the register allocator needs to allocate registers to such a temporary, it will have to move some others around. After that, we eliminate SSA and lower it to hardware instructions completely. After that, there's some hardware-specific stuff that we need to take care of. We need to insert some base states and knobs, resolve some hardware hazards. And finally, we are already pretty close to the GC and rDNA assembly, so we just encode that for your hardware, and we are ready to go. So that's how ACO works. And now I'd like to show you a couple of examples of how we had to change it in order to be able to make it the default compiler. There were lots of features missing. I think the prime one is supporting new hardware. Or, well, I could say hardware that is new to us, at least, because some of these are actually pretty old. This was actually my first task when I started working on ACO. I dived straight into the defaulter by starting to work on Navi support. And later, other people, I think Sam worked on GFX6 support, and Daniel on GFX7. So a couple of takeaways from adding support to new hardware is that the compiler code gets just more and more hairy as time goes on. That's because the different hardware generations have different assembly encodings. So even though they might have the same instructions or some variations of the same instruction, those still have to be encoded slightly differently. The other thing is that there are some instructions which were present on Polaris and Vega, but they were missing from older hardware. For instance, the really old GPUs don't have loads that load 3 32-bit values. So that was something that we had to work around. And there are also instances where some existing instructions were removed from newer hardware. The other interesting issue is that those really old pieces of hardware don't really have any subgroup features. So what this means that when multiple SIMD lanes have to cooperate with each other, there are no dedicated instructions for that, or at least there are no sophisticated ones. So we have to actually emulate some of those features. And of course, if you get any new hardware, you also have some new hazards that you have to mitigate. But one very, very good thing that I'd like to highlight here is that we have a very helpful community. So as soon as I started working on Navi support, there were some guys that popped up and started testing it. And I was pretty shocked because, well, when you just started working on something, you have some code, lots of stuff that you still have to kind of figure out. But there are already a couple of guys there who are submitting issue reports and whatnot. So they were very enthusiastic, and I really, really appreciate that. We love getting bug reports from you guys. I think the most difficult part, however, is supporting small bit sizes. So what we had previously was that we supported 32-bit and 64-bit values in ACO, and basically nothing else. Because, well, who needs anything else? Turns out lots of games do, and the spec does also. So we needed to come up with a plan. What should we do about this? I mean, if you want to support 8-bit values or 16 bits, what can you do? And well, we are a very creative team. We had a lot of different ideas. I'm not going to detail them. I am going to just say that there was one thing that was common between every idea. We had lots of bad ideas. That's because there are lots of edge cases in these topics, and there are more exceptions than rules. Lots of different things that you need to take care of. So after some discussion, we decided, well, this is mostly just a question of where you put those 8 or 16-bit values. How do you assign them to registers? So let's just push the entire thing into the register allocator, and that will be fine. That was the best idea that we could come up with. However, there are some interesting challenges that arose from that decision. One of them is maintaining the register file. What we had previously was we had a number of known registers that we had. Those were available. We could allocate them. But now, how it works is that instead of allocating registers, we allocate bytes. So not only can we allocate a register, we can allocate a byte within a register to some temporary value. And this is a genius idea, but it increases the burden of how we maintain the register file. Obviously, there are some concerns of memory usage and such, but we were able to solve this quite efficiently at the end. The other consequence is that those shuffle instructions that I was talking about earlier, when you move around different values between registers, those are now crazy. They are bonkers. So previously we had to move registers or the contents of registers to other registers, and basically that was it. But what we have to do now is that we have to move individual bytes. Sometimes we have to move those bytes between registers. Sometimes we have to move them around within the same register. So you can imagine that there's lots of special cases in the code that we had to get around to. And if we have to move bytes within the same register, then that also means that we have to take care not to overwrite our own stuff before we actually move it where we want it to be. So lots of interesting cases there. And the other point about small bit sizes is that support between different hardware generations is quite inconsistent. So some of the newer hardware has dedicated instructions for working with small bit sizes. This is called SDWA. But it works a little bit differently between the generations. Some of the hardware, when you work with the lower bits, it just leaves the high bits alone. Some other hardware will override the high bits. And of course, on older hardware, you have to manually do it with bit shifts and bit multiplications. And well, there is lots of tricks in the books that we have to use here. So as we expanded on these features, we had to also expand on the supported shader stages. And I think the first milestone that we had in this regard were geometry shaders. And with geometry shaders, there came a number of new headaches that we hadn't dealt with before. So obviously, we had to add support for lots of new intrinsics. We had lots of things about I/O that we had to figure out. And we also had to understand how merged shaders work on your hardware. So we have 4 new stages. So on the older hardware, every software stage has its own hardware stage. So that's pretty straightforward. But on newer hardware, these are merged into just a single shader program. And you might ask, well, how does that make any sense? Since the number of shader invocations is not the same. So how can you merge those? And also there is this little issue that pixel shaders can't really read the outputs of geometry shaders directly. So we had to add some glue in there to make that possible. And this is called the GS copy shader. So just to illustrate what we had to before, basically if you have a simple vertex shader, it will execute a couple of instructions and then it exports its output to a buffer where the pixel shader can read from. What we have now with geometry shaders is that vertex shaders have to store their outputs to VRAM. The geometry shader has to load those from the VRAM. And then it also stores outputs into a different place in VRAM. And finally, since the pixel shader can't read those, we have to run the so-called copy shader in order to copy those into the buffer where the pixel shader can read from. So this is for old hardware. For new hardware, the first 2, so the vertex and geometry stages, are merged into one. And well, the good way to think about that is that those are still separate shader programs. They are just kind of bolted together. So you have 2 halves of the same program, and each half is prefixed with an if statement, basically. So the shader asks itself, well, is this a vertex shader invocation? And once it figures out that, then it also asks itself, well, is this a geometry shader invocation? And if it is, then it also executes those parts. But of course, it still needs the copy shader in order for it to work correctly. Yeah. So the interesting part is that this is eliminated by NGG. So that's a little more efficient in this regard. And the other big topic in order to expand our support of shader stages is tessellation. So when I first started working on this, I was pretty surprised to realize that tessellation shaders don't actually do any tessellation. So what actually does the tessellation is the hardware fixed function tessellator unit. And what the shaders do is that they kind of just feed this fixed function unit. So with that in mind, we still had to add support for a bunch of new intrinsics. And of course, the thing with the shader stages gets more and more complicated with new hardware as well. And we had some really good brain puzzles for I/O. So with regards to merge stages, here the vertex and tessellation control stages are merged on your hardware. And if there is a geometry shader, then that's also merged with the tessellation evaluation shader. So we had to kind of add these concepts to ACO. So we added 6 new stages in order to take care of this. And the interesting part is that as opposed to the geometry stage, we could now use these merged stages to do some optimizations. So the interesting thing is that it's possible for the vertex and tessellation control shaders to have the same number of invocations. And this mostly happens when the input and output batch size are the same. Usually this is 3. And it turns out that this almost always is the case for the majority of games out there. So when we detect this, we can eliminate vertex shader output stores and just transform them to temporaries. So what that means in effect is that we use registers instead of memory. So writing registers is, of course, much faster than writing into memory. And I mentioned that we had this puzzle, the I/O puzzle, that we had to figure out. And the main issue here is that tessellation control shaders can also read their output. So previously what we had were shaders that could read the input, their input, which was the output of the previous stage, and then they would write their own output. But that was basically all. There was no I/O going on in the middle of the shaders. But now with tessellation, there is. And what this means is that we also have to optimize for these. So a tessellation control shader, for example, can have outputs that it reads itself, and it can also have outputs which are just read by the next stage. So for the next stage, we have to store the outputs to VRAM. When the shader reads it by itself, then it has to be stored in LDS. For those not familiar with AMD hardware, LDS is an on-chip kind of memory. So it's much faster than VRAM, but also limited. And of course, these work differently. So we had to use 2 different memory layouts for each. And finally, we also added support for the new Wave32 mode that was added to the Navi hardware, which means that as opposed to previous hardware, which had 64 SIMD lanes, which means it would run 64 shader invocations in parallel, we could now optionally have only 32 of those. And this is good for lots of cases. It's advantageous in more divergent shaders, and some instructions are simpler, and so on and so forth. But it kind of feels like when you're climbing a tree, and it turns out that while you're climbing your tree, someone is cutting it out from under you, because this thing breaks a lot of assumptions that we had earlier. So we have these special registers. I already mentioned exec briefly. VCC is also a similar one. And these are always 64 bits on older hardware. So now we have to kind of change every usage of these registers to either 32 or 64, depending on which mode the shader is running at. And another interesting one is Booleans. You might think that Booleans are simple, and that's going to last as long as you start working on a compiler, and then you realize that they are not. What we had before, we had 2 kinds of Booleans in ACO. So first we had uniform Booleans, which means that all of the threads agree on the value of the Boolean. And for this, we used a single 32-bit register. We also had the kind of Booleans where the threads disagree about the value. This, of course, since we had 34 threads, we needed a 34-bit value. But if you transfer your program to Wave32, then suddenly you only have 32 threads, which means that a divergent Boolean is also 32 bits. And then all the code that depended on whether or not the size of the Boolean is 32 or 64, well, all that logic just goes down the toilet as soon as you start doing this. So we banged our heads against the wall for a while. And finally, we came to the solution that, maybe this uniform versus divergent thing, it was a little premature. So let's just have only one kind of Booleans, and those should be per lane, which means they kind of correspond to the divergent Boolean that we had before. And if we can prove that a Boolean is uniform, then we optimize that back to the same instructions that we had before in our optimizer. So in effect, what we did was, in order to make it correct, we kind of had to screw up our instruction selection and make it less optimal. And then we kind of shoved all of that into the optimizer to make up for it. Also, if some of your shaders can run with only 32 lanes and other shaders with 64, then what's your subgroup size? So the Vulkan API makes it possible for the app to query the subgroup size, but what should you answer to that query? And this is something that we debated extensively within the team. And we came to the conclusion that we should always report 64. And in Wave32 mode, we pretend that 32 of those 64 are always disabled. This is, of course, somewhat of a lie, but it conforms to the spec. There are slight issues with some non-conformant apps, but let's not get caught up on unnecessary details here. One thing that we still kind of have to figure out is when to use Wave32. And as far as I know, this is a question that the developers of Radeon SI also struggle with. Currently, it's always off by default, unless you use an environment variable to use it. And I can assure you it will work. I played Shadow of the Tomb Raider through with Wave32. But it's not universally better. It doesn't always perform better. Of course, there is this Vulkan extension, which lets you choose it for compute shaders. So that's available. For vertex, tessellation, and geometry, we will have to come up with some kind of a logic which will decide which mode to use, maybe based on the divergence. And for pixel shaders, it's completely out of the question. It doesn't perform well, thanks to how interpolation works in the hardware. While we were at all of this, we also fixed some bugs too. We have an awesome community who reported lots of issues to us. So big shout out to you guys. And in order to make sure that as few bugs happen as possible, we also added a testing framework. Let's now talk a little bit about what's in store for ACO in the future. Of course, the work never stops. I think perhaps the most important thing that everyone's curious about is support for the new RDNA2 GPUs. And I can tell you guys that we are working on this. Of course, there is no public documentation from AMD yet about the new architecture, but Radeon SI and LLVM already have some code for it, so we can browse that and use that, and we already do. The other thing, I think this is the most popular request that we get, is we should support OpenGL. And yeah, we want to support OpenGL and somehow add support for ACO to the Radeon SI driver. Sadly, this is not as easy as just copy-pasting some code here and there. So it's, I guess some people think it's a simple thing. Why didn't we already add it? But sadly, it's not as simple. It's a pretty long road. We already started on it, so I think Connor had a merge request which unifies how shader arguments are handled between Radeon SI and RADV. And Marek works on unifying the I/O handling between the two drivers. So this is some very good progress on this front, but sadly, ACO still depends on some internal behaviors from RADV. And we have to figure out how to make it independent from RADV before we can support OpenGL. The other interesting thing about RDNA2 is hardware accelerated ray tracing. And for this, there is already a Kronos extension. And also there is some LLVM code which was published, I think just yesterday. But we don't have any public documentation on how the hardware actually works yet. So it's kind of a trial and error thing for us. There are also mesh shaders, which we are interested in supporting. And as far as the hardware goes, we think that it's possibly doable even on the currently released Navi GPUs. But of course, there is no Kronos extension yet, so I can't say for sure. And there is always more optimizations on the way, so if you feel that your game is slow with ACO, you don't have to be afraid you won't be left in the dark. So a couple of things is rapid packed math that Daniel is working on, and we have loads of improvements on the way. So thank you guys for listening. I think the job of a compiler developer is never really done. Sometimes I kind of feel like the little hamster or squirrel which just runs in circles within a wheel. There is always something more to do. So thanks for listening. And do you guys have any questions?
Yes, can you hear me, Timur?
Yes, I can.
Okay, very good. I had an issue with my voice and the mic. So the first question was from Jason Ekstrand. Which 15 shader stages? So he was confused where these 15 came from.
Right. Okay. So so in ACO, the stages are not exactly the software stages that are in the Vulkan API, but rather the combination of hardware and software stages. So on other hardware, every software stage runs on a different hardware stage. So that's a pretty obvious mapping. But on the newer hardware, we have these merge stages. And in ACO, we have to handle each of those cases separately. So as far as ACO is concerned, we really do support 15 different stages. I guess from the API standpoint, you could say that these are maybe 15 different combinations of software and hardware stages. Did I answer your question, Jason?
Let's wait for the answer. There's a 5-second delay. So in the meantime, Simon Sir is asking, in the end, would you say it was worth it to add all the complexity to support Wave 32, given the benefits are unclear?
Well, that's a hard question. So I have kind of I am of two minds about this. So first, from a compiler development point of view, I think it's a useful exercise to add support for more stuff, because then your code and your design becomes more flexible, and I think that's always a good thing. On the other hand, of course, I think it's not always apparent when to use Wave 32. So if you look at it that way, you could say that it's useless, kind of. But it's not going to stay useless forever. So I mean, we still fully intend to figure out when it's beneficial and then utilize it, if so.
Okay. The next question is, Jason said yes, you answered this question properly. Then the next question comes from, wait a second. I don't have his full name at hand, but with Zinc doing OpenGL to Vulkan, I was curious why direct OpenGL support is being considered for ACO.
It's ACO, not ACO.
Oh, yeah, sorry, ACO.
Sorry.
No, you're right.
Yeah, well, the short answer is that you can find some benchmarks about Zinc versus Radeon SI. And I really love how Zinc works, and it's a good effort, but it doesn't perform up to par with Radeon SI. And I think that as long as someone is willing to invest in making Radeon SI perform as well as possible, I think as long as that's true, Zinc will always be somewhat behind in performance.
That makes sense. Could Wave 32 still be beneficial for fragment shaders that do very little varying interpolation, like full screen quads that retrace scenes, etc.?
Maybe. So the thing is that we didn't exactly have a good way to test this yet. So what we would need is to classify the shaders in some way, like how many interpolation, how much interpolation does it have to do, how divergent is it, and if it's very divergent and it doesn't do that much interpolation, then I think the answer to your question is yes. But the problem is that it's kind of hard to tell those things in advance. So the practical answer is not yet, at least.
Yeah, this is something that Jason could also talk about at Intel. With Sims 32, it's somewhat the same issue. Like, yeah, some shaders are benefiting, but then knowing which ones is tough. We have another question from Luke. How much of ACO is specific to AMD? If we wanted to add a different GPU architecture, what would be the challenges?
Yeah, sorry. I think that you could use the concepts in ACO. You could use some of the ideas from ACO, and you could reuse all the principles, but you could reuse almost nothing from the actual code, because ACO IR is basically, as I said, almost the GC and RDNA assembly language. So if you want to kind of add support for a different architecture, that would mean that you delete ACO and add another backend, basically. So ACO is already a backend, so it doesn't make sense to add another backend to a backend. But if you look at it from a higher level, I think what we do with ACO, other people are also doing with their own architectures. So I hope that answers the question.
Yeah, I think so. We do not have any other questions so far, but someone just joined, so maybe a question is coming in the next seconds. If not, then I guess that will be all. Thank you, Timur. And the next presentation is going to be about etnaviv by Christian in 11 minutes and 30 seconds.
Christian, the stage is yours.
Yeah. So, hi, welcome. I would like to talk about the current state of etnaviv. You might ask yourself, who's this guy in front of the webcam? My name is Gmeiner Christian, and I'm a long-time etnaviv developer. I live in Austria, near the Lake of Constance, and no, we have no kangaroos. I'm a first-time XDC speaker. I talked the first time in public about etnaviv, so I'm a little bit nervous, but I hope we get through it. So let's see what's on my agenda for this little presentation. First, I want to talk a little bit about the history of etnaviv, as there might be some facts that you did not know until now. Then I will talk about the state of etnaviv, followed by a topic that I'm currently into, continuous integration, and about the future of etnaviv. So let's have a look at the history. Everything started in the year 2012 when Rajneesh Bhardwaj, I hope I pronounced it correctly, to work the etnaviv binary block. And I don't know why. Okay, on my side. Okay.
Yeah, so for information for the stream, we had some bandwidth issues and we're just going to cut webcam quickly, and it should help with the bandwidth problems. So you can continue and I'll let you know if there are any other problems.
Okay. So yeah, 2012, everything started, and I'm not sure why, but in late 2013, I got interested in the black magic of GPU driver development, and I found out that etnaviv was going on. So I started hacking on it, and in October 2013, I contributed the first patch. It was nothing too fancy, just some compiler fixes, I think. Later on, I worked on basic bring up for the GC2000, which is found under IMX6. And there was a basic new concept. The first GPU we supported with multiple pixel pipelines. And it took me quite some time. I started with something like this picture. And after some hours, days, weeks of hacking, I finally was able to get GLX gears rendering the correct thing. Followed by GL Mark II, and some super simple application started to work on GC2000. Wonderful. The next thing, all this reverse engineering happened against the GAL core kernel driver provided by Vivante. And it was clear to move forward, we need to have our own kernel driver to handle the hardware. And 2014, the guys started hacking on a kernel driver. And it took some time, about a year, I would say, until the etnaviv driver landed really in the upstream kernel. If I'm not wrong, it was in version 4.4. And so we could start working to upstream etnaviv in Mesa. This took about a year, and then finally in February 2017, in Mesa 17.0, etnaviv landed. Wonderful. If you ask who the guys are or who the persons were that attacked on etnaviv at that time, for sure Vladimir. Then there was a lot of contributions and work from Russell King. Lucas Strach did a lot, and maybe 1, 2, 3 other peoples I forget at the moment. The biggest challenge with etnaviv was that etnaviv GPUs are only render-only GPUs. So the kernel mod setting, the scan-out part is separated from the acceleration part. And it took some time to get the basic functionality, the infrastructure ready for render-only GPU drivers. And it is still in place, and the library in Mesa is called render-only. So from there on, we worked to fix bugs, support new features, and currently, we support a wide range of different GPUs, starting from smaller ones like the GC600 up to the GC7000L found in the Freescale IMX8M. The wonderful thing about the etnaviv GPUs is that the shader either did not change dramatically, so we can support all different ranges of GPUs with one compiler. And the Vivanti GPUs use some kind of feature bits, which makes it quite easy for us as developers to support new features on a GPU. So we don't need to take care on our own to figure out what changed in the specific GPU core, but we can trust more or less the feature bits. Later on, Vivanti itself changed the way how they work with the feature bits. They went from the feature bits provided by hardware registers to a hardware database, where they look up the correct feature bits based on the GPU revision and some other IDs. So that makes it really, really easy for us to support multiple different GPUs. You might ask where those fancy GPUs get used. For instance, the GC7000L is used in the MMT reform, in the Libre-M5 Purism, and the other ones, especially the Freescale-based devices, are mostly used in industrial applications, for instance, in airplanes. So at the moment, etnaviv is more or less a Glass 2 driver. We support desktop GL version 1.3. And if you use the experimental near backend, you get desktop GL 2.0. At the moment, TJSI is preferred over near. etnaviv is shipped in distros, and sadly, there are not that many developers around etnaviv, so it takes a little bit longer to get stuff done. But more or less, we are now in a state where stuff mostly works. I often get the question, how fast is etnaviv compared to the binary blob? Here are some numbers I got from Chris. Hi, Chris. Where you can see that we are not that bad. That's the overall GL Mark II numbers, the final numbers compared. And we are almost on par with the binary blob. In most cases, we are much better than a binary blob. There are some problem areas on different types of GPUs. For instance, we have some problems with texture filtering speeds or some shader issues where we lost a little bit of performance compared to the binary blob. So now I want to switch over to another big topic of mine that I'm currently looking into. That's the continuous integration. I'm in the situation that I'm more or less the last active developer for etnaviv that's doing regular work. And when I get patches, I often end up in a situation that I'm not quite happy with the patches, and I would love to do a wider tests on different GPUs, as I don't want to regress that often. That happened sadly in the past, and I really want to get etnaviv to a more stable base to work on, to trust. So I looked around what Mesa currently uses for continuous integration solutions. There are the Lava-based ones and bare metal-based ones from Eric. Firstly, I tried to look into the Lava-based ones, but the setup and the magic that you need to do is too much for me. And I started to look into the bare metal solution. I contributed some patches, and currently it runs. It is Docker-based, which I love. I decided to use my Unraid-based NAS for the GitLab runner. I use CR2net for console logging on a Raspberry Pi, and I use ETH-based power network control, as I'm really focused to have it as flexible as possible for me and as simple as possible from a setup point. This is a picture I took, not sure, 1-2 months ago, where you can see my basic test setup. It is really not much. Some devices on the test. On the bottom right side, the network powered power control, and the Raspberry Pi on the top for the serial communication. What is missing to go live with the etnaviv-based CIA solution? There is an open merge request for disk shader cache, which hopefully someday soon will land. This improves DPQ run for about 2 minutes, which is quite nice. At the current state on a GC 2000 based GPU, a full DPQ run takes about 7 minutes, which is quite okay. Also, to go fully productive, I need to do some VLAN setup on my side to be safe. The hardest part is to get it a little bit more stable. There are some concurrency problems I need to look into. There was a patch from Lucas Dach that landed in the kernel lately that helped a lot. There were some interaction problems with the GPU scheduler. So I'm getting there. And I want to hook up some more devices. As you can imagine, I have a lot of devices here at home. And I've planned to hook up at least 2 IMX8M based devices to really start through. The future. The biggest point for me after continuous integration is to finally promote the NEAR-based experimental compiler to a stable level. As NEAR produces about 30% better shaders than TGSI, but lately the NEAR compiler turned into a little bit rotting, and let's see. I really hope to get it into the next Mesa version. Then I would like, or the guys working on etnaviv would like to see Class 3 support. There was some work done that got a little bit stopped due to this whole COVID situation at the moment. And we need really to look into get stuff fixed on the different GPUs so that we have a nice baseline where we can add new features onto. And so much more. you can imagine what's else left. You can look into compute, you can look into performance optimizations. There's so much to do and so less manpower to work on it. So I think I'm now done. I'm in time and I'm ready for your questions, if there are any.
Yes, we have a question from IRC, or rather more like a statement. So quoting, concurrency issues? Yeah, better tackle this as soon as possible. We still have to fix it in Nouveau. DEQP has quite a lot of tests to verify it all works.
Yeah, that's correct. I'm mostly interested to get DBQ stable, also the flanky ones, but it is really hard to debug some of them. If I run in a non-parallel mode, I get no GPU hangs and the world looks much better. So there's really some stuff to look into.
Okay, we've got another question. What's the biggest problem holding the near backend back? Just time?
Yeah, mostly regressions. I have some compiler tests, mostly some TGSI shaders, which are completely failing at the moment. Also, there are some asserts starting to hit from time to time in the near compiler, but it's not that much. So I really hope to land it in the next Mesa version.
Okay, I don't see any other questions. Thank you very much, and I'm really looking forward for you to enable your farm for other people. So thanks for doing that.
Me too.
And we have another presentation from you in 13 minutes. So we're going to take a break and we're going to be back with Christian. See you soon. Christian, the stage is yours.
Yeah. Hi, welcome back to another wonderful etnaviv talk. This time I would like to talk about the wonderful word of performance counters. If you missed my talk before, my name is Gmeiner Christian. I'm a long-term etnaviv developer. I live in Austria near the Lake of Constance, and there are no kangaroos. So I'm a first-time speaker, and I hope to get it right. So let's start. I want to talk about GPU performance counting in general, then the specific thing about etnaviv GPUs in that regard, how the binary blob solves it, how we do it in etnaviv, and what feature topics we have regarding performance counters. So I think everybody of us knows this situation where a random person hits you up and tells you, hey, my application is running slow. What shall I do? And I'm in that situation and I tell the guy, I'm not really sure. It can have multiple causes why this application is performing bad, and it can have multiple causes why it's performing better than the binary blob. For instance, we could miss some extension, etc. support in etnaviv, or we are simply doing too much stuff. We do an extra blitz where no blitz are needed, or stuff like this to waste too much bandwidth on the system. So for this, we can use performance counters. They can help to analyze the performance and execution characteristics of applications. Wonderful. I think that every major GPU manufacturer has some tools to visualize such performance counter traces. In my case, or in an etnaviv case, there is a vAnalyzer application where we can look at the different performance counter values and try to figure out what goes wrong. So there's now one special thing about the GPUs from Vivante. This is a really hard one. You cannot access the performance counter registers values from the command stream. There's only one little exception to this, the occlusion queries, where you can really define in the command stream the address of the occlusion buffer where the hardware should write the actual value. In a normal case, there should be a way to access the performance counters from the command stream, because it helps you with a lot of stuff, which I'll go into deep a little bit later. But during the preparation of this talk, I found out that there might be support for this feature in the coming GPU generations, because there is a feature flag called GCV feature probe. And if you look closely into the public Git repo for the Linux IMX tree from Coderor, you find some interesting informations. Sadly, I have no GPU which supports this feature, so it's something for the future. So, as we know now the limitation of the how we need to, or how we can access the performance counters, we need to work on a solution to provide the performance counter configuration values to the user space in the end code. So with that knowledge, we know that only the kernel can access these registers. There are some simple performance counter registers where you just read the register and be safe. Then there are more complex registers where we have a multiplexer, where you need to configure the multiplexer to select the wanted performance counter source. And then you have a separate register where you can read out the selected performance counter. And there's another special thing where you have multiple pixel pipes, you need to iterate over the pixel pipes and do the max config read-write thing to get the per pixel pipe specific value. And you need to take care of stuff like clock gating, and you need to enable debug register access for some kind of performance counters. So it sounds quite easy to implement this, or let's move on how the Vivante provided Galcore kernel driver does this. As I told you before, you need to enable and disable the profiling mode to ensure that clock gating is disabled and that the debug register access is enabled. And for this, the Galcore kernel driver provides some commands, the get profile setting and set profile setting, to switch on and off the profiling environment. Then there's another command that allows you to define what should happen if you have read the performance counter value. Should it be cleared or not, for instance? So now we know how Galcore configures set up the performance counter context. Now we need to read out the performance counter registers. And for this, the Galcore interface uses 3 other commands. One is specific for the 2D core. That's the profile registers 2D. And then for the 3D core, we have a profile registers part 1 and 2. So with that in mind, the hardest part for etnaviv is now to figure out the MUX configuration. What MUX config relates to what kind of performance counter value. The good thing is that Galcore also is a nice register documentation. For instance, if we look here at this excerpt from the Galcore driver, let's say we want to read out from the pixel shader how many branch instructions there were during the overall runtime. We can look it up in the kernel driver they provided. We can see here that we select the correct, hopefully correct MUX configuration. We select a certain signal, I call it, and we configure the MUX. And later on, we can read out the selected performance counter value. So quite hard to read such obfuscated code, but it works in the end. You know what to look for. And the thing with Galcore is that over time, over new releases in Galcore, they add new unknown performance counters. So it's also always nice to have a look at the kernel driver source code to see what's going on there. So now we have a rough picture how the performance counter readout with the binary blob could work. It looks like that there's some cyclic event readout triggered, and that all performance counter values are read out and stored to some magic file where the VAU analyzer application can look at it and present results, and the developer is happy. So now we need to come up with something for etnaviv. There are 2 ways to approach this. We can go simply the way Galcore does it, which means we have one I/O control and read out all counters in one go. Sounds simple, but is it the right solution? From a development standpoint, it is really easy to implement. You have 2, 3 I/O controls you need to support, and you simply read out everything. Quite easy. But there are, from my point of view, some problems with this approach. For instance, we need different I/O controls for different pipes. Pipe is a concept called used in etnaviv. A pipe can be a 2D core, a 3D core, or VG core. And the approach the GL core interface has chosen is to have different I/O controls, commands per pipe. And I'm not really happy with this design decision, but I could live with that. The next one is a little bit harder. You need to be ABI compatible if you add newer counters. The nice thing about GL core and the binary driver is that they are tightly connected to each other. If you run GL core kernel drive in version X, you need to use the GL core binary blob in version X so that they work together nicely. The Vivanti team does not care about ABI compatibility. So the next problem with this whole approach in sampling, cyclic sampling, one-shot sampling, or I'm not sure how I should call it, there is really no relation to a specific draw call. And I think that is a quite important thing. If you want to analyze one frame and see what the GPU is doing, it is much more helpful than having a rough overall state. Because keep in mind, the CPU and the GPU are not synchronized to each other. So the time when you sample the performance counter values in one go might not really reflect what you're looking for. It might be before your draw call, after your draw call, in the middle of the draw call. So you only get the rough overview picture of everything and not the really zoomed in way into a one draw call. So that was no way for me to add support for performance counter. So I needed to come up with a different solution for the same problem. How about emulating the missing counter access from the command stream? It takes much more time to get it right, as we want to be stable API and ABI-wise, but it can be done. One plus point would be we have one interface for every kind of pipe. We can use the same mechanism for 2D, 3D, and VG cores. We can easily extend new known counters without breaking any ABI, as we have no fixed offsets where one counter needs to lie in memory. We have no limitations in size of the structures used, etc., etc. So another plus point. And the biggest for me is that if we can emulate a register access from the command stream, we can easily get the relation between a specific draw call, which is super helpful in my eyes. And also, if we go that route in emulating the missing counter access via the command stream, we can easily support the so-called one-shot readouts like done by the GL core kernel driver. So how can we do this emulation in a command stream? etnaviv kernel driver uses an in-kernel command buffer, a secular command buffer, where it queues in, or it jumps to the user-provided submit I/O controls command buffers that you get from the user space. And in between there, we now do stuff. We do cache maintenance, we do pipe switching stuff, and we can also do something to emulate this readout of the performance counters. So in order to the hardest part is to get everything synchronous. Also that the GPU and CPU are doing the same. They are halting at they have the same expectations where the GPU is. For this, we modify the in-kernel command buffer if we queue in a user space buffer, and we trigger an event, which is the same as an IAQ on the CPU side. Then we stop the FE. The FE is the fetch engine. It's more or less a fancy DMA controller responsible to process the command stream. At that point, we know now that the GPU isn't doing any rendering stuff, etc. So we can now process the IRQ on the CPU side and do some work in the driver, whatever this work might be. If we are done with this work, we can easily restart the fetch engine and everything continues like before. This sounds quite terrible in the standpoint of performance, but I think that when you're doing performance counter measurements, you're really interested in correct numbers and not in the overall performance of your application. So yeah, and this whole thing in the etnaviv kernel driver is called a sync point. So we have now the possibility to really stop the GPU at the defined state or the defined position in the command stream, do some actions, and move on in the processing of the command stream. With this little trick, we can easily do the emulation of the performance counter readout in the command stream. In order now to make use of this mechanism, we need some kernel interfaces to provide access to the performance counters for the user space. We need to get the list of possible performance counters. We have chosen the way to store the possible or the available performance counters on the kernel side, as there might be some hacks, some changes over the lifetime to read out a specific register, a specific performance counter value. Then you can do the correct logic in the kernel and don't need to do a lot of dancing in Mesa. We need a kernel interface to configure the readout, hopefully via the submit IO control. And we need some way to expose performance counter data to user space. So let's start with the simple one. The simple one is we need an interface to define all possible performance monitor domains and signals. We have chosen to put this into the kernel, and we have one big structure where we, for instance, in this case, we have a performance monitor domain called SH, which has 9 signals, and I have put one of them here on the slides, the shader cycles. And as you can see here quite nicely, we have in the domain struct part, we have a profile read where we define which register is used to read out the selected max value. And we have a profile config field, which defines which register is used to configure the multiplexer. And in the signal part, we have a struct member describing which value needs to be written to the multiplexer configuration. And also we define the name and how the readout should happen. If you remember, we have 3 different cases for performance counter readouts: the simple register read, then the max read, and the pixel pipe readout. So now we need to define the IO control interface for this. And we have one part to query all performance monitor domains. for a specific pipe. Remember, a pipe can be 2D, 3D, or VG. And we get per the domain the name and how many signals the domain have. And then with that information, we can query the different provided signals for a pipe and domain combination, and we get the name of the signal out of this interface. The next part would be the user space now has access to all counters that are possible to use. Now we need a way to provide a mechanism to read out these performance counter values for a submit. A submit is basic, so we need to have two different positions where we do the processing of the performance monitor readouts, because we want to read out the performance counter before we do the actual draw, and we want to read out the performance counters after the actual draw. That's the two defines the process pre and process post. Yeah, and then we need to define a sane way that the user space has a possibility to store a selected performance counter value at an offset in a provided buffer object. And we need to provide a way to define when the sampling of these performance counter values should happen. With that, we can extend our submit IO control. We can now specify how many of these performance monitor requests we want to execute for this specific submit. This makes it possible to sample a well-defined number of performance counters. So we don't need to read out all possible performance counter values, but we can specify we will only want 2 or 3 of them. With that, we have now a pretty sane, in my opinion, sane interface for the user space to work with this kind of performance counters. Now the next thing is, how should we integrate this into our Gallium driver? We went that way that each pipe query has its own buffer object. Remember that in the submit IO control, we just define the number of performance monitor requests, and in every request, we define where to store, at which offset of the buffer object would you like to store this specific value. That's why we have, that's why every pipe query has its own buffer object. Then we implemented the begin query, end query, get query results to work with the performance counter monitor, which means when the begin query function is called, we simply add a performance monitor request to our submit IO control, to our submit structure. We add a performance monitor request to the submit, where we define that we want to sample it before the draw starts. And the same happens for the end query, but we add a performance monitor request to the submit with the sampling time post, which means after the frame has been drawn or the draw job was executed. With this, we can now really sample the performance counters before and after we do the draw. Now, the interesting part is, how do we get the results back? Basically, we do a CPU prep to get access to the buffer object, and there's a little trick used. Every time we add a performance monitor request to the submit IO control, or that's the submit call, we define an expected sequence number. And when the kernel part processes the performance monitor request, it stores the expected sequence number at offset 0 in the buffer object. With that, we can easily check if our query is done or has a result, let's call it that way, by checking the sequence number. If the sequence number matches the expected one, we can simply process the written values and do our stuff. And after that, we call CPU fini to give the buffer back into the GPU domain. And now we have one simple problem. We need to take care when flushing happens, because we need to stop the active queries, flush the buffer, and begin again. With that in mind, we store multiple value pairs in a buffer object for one query. Now we have everything hooked up into Gallium API, which gives us the possibility to use the Gallium HUD to stare at the performance counter values to get nice graphs, how they evolve over time. And also it is possible now to use the AMD Performance Monitor OpenGL extension to interact with the performance counter values provided by the GPU in a same well-defined interface that can be used by tools, which is really, really nice. So we have now the basic stuff laid out, everything works, but as you can imagine, we are not done yet. There are a lot of stuff that is interesting too, besides the basic performance counter values. One of them is the load values per, call it engine in the hardware. And there is work in progress thing I got here running. You can see here the Gallium HUD showing the load values of different engines, different engines for different use cases, or different scenes rendered here. This is mostly work in progress at the moment, as I had to talk to a lot of guys how they are doing it for their hardware, because I was not really sure how to model the user space, kernel space interface, as the etnaviv GPU has one idle register where each bit represents one of the engines here. So I wanted a sane interface, and this takes time, but I hope to land support for this quite soon. Another interesting thing that would be nice to have are bandwidth values. There are performance counter registers or MUX configurations to read out, for instance, how much bandwidth does our fetch engine consume, how many blit reads are we doing, and stuff like this. The biggest problem here is, again, getting the kernel user interface right. I could expose these values by the current Perfmon infrastructure, but I'm not really sure if this is the right thing to do. Also, I need to verify what happens if these bandwidth counter values overflow, if I need to reset them or not. And yeah, what also blocks me at the moment is that I'm not perfect in handling big patch queues. So I try to land one thing after another and don't want to do much in parallel. But I think with these bandwidth numbers, we also get a much better insight what's really happening, or what is really happening inside the GPU, and where we can take steps to improve the performance. Another topic that got a lot of attention recently is this thing called Perfetto. This is system-wide profiling thing where you get a really, really nice overview what's happening in your system. There is some proof of concept, I might call it. I'm not really sure, but there's, I think, pan-first support at the moment for the performance counters, and I tried to hack in order to hack etnaviv support, but at the time I looked into it, the Perfetto GPU integration was really fixed on pan-first, and in my eyes there's a little bit work needed to support different GPU providers. But overall, I have work in progress patches to support this feature too. Now, in contrast to the per frame performance counter values readout, Perfetto works on like the GAL core profiler. So you do a cyclic reads out of all the interested performance counters without a really relation to a specific draw, to a specific frame. And yeah, I hope that we can land support for Perfetto too. There are work in progress patches. Basically what we are doing at the moment, we are enabling and disabling the power gating and the clock gating and the debug register access on the fly when we need to process a performance monitor request. In order to support Perfetto, we need something like the GAL core kernel interface has. We need a way to enable a global profiling mode where we turn on the access to the debug registers and disable the power gating overall for a longer period of time until it gets disabled. Yeah, and there are work in progress patches to support these scenarios. Another interesting thing to support Perfetto is how should we expose the red performance counter values? Because currently we are using buffer objects to let the kernel store the values in there. So we would need here another sane interface that supports the readout of a handful of performance counter registers values, and we need you use normal system memory instead of a buffer object. But in the end, I see no big showstopper for Perfetto support. So overall, we have, I think, now a really great picture how the performance counter stuff on etnaviv works. And I was really happy that I got contracted to do this work. And I think it turned out quite nicely. It was, at the beginning, I thought it would be a lot easier to get stuff done. But with all the special cases you need to take care, it took a little bit of time. But I'm really happy that everything landed is in the upstream repos. You find it in the kernel repo, in the Mesa repo. So you really can consume performance counters on etnaviv. Sadly, I was a little bit too fast. So thank you, everybody, for listening to me, and I am open for some questions.
Thank you very much for your talk, and let's see if we have any questions on IRC. So I just see, I know that yes, the Perfetto GPU collection does need to be a bit more generic. Patches extremely welcome. And another note that even NVIDIA isn't that bad, so...
Yeah.
So I guess that's it. Thank you very much for your talk. And the next talk will be by Martin Perez. Martin, can you do the switch? Yeah, he's a little bit busy, so about that.
Hi everyone. Hopefully everything is working. Just checking with the stream. Yes. Okay. So today I would like you to talk about LiteDIP, which is bridging the gap between, or hopefully bridging the gap between open hardware and open OSs, and with a nice repetition on the word between in the talk. My name is Martin Perez. I'm currently working with Intel, but this is a very personal project. So this is really just a hobby. So the agenda for the talk is gonna be, so why start a new project? Then why is it about FPGAs and why people should care about this now? And then basically what is missing currently in the FPGA world or the ecosystem. And then finally, what is LiteDIP? So sorry for the lack of animations. I just finished the slides and didn't have time to enable animation. Or some of them have it, some don't. Sorry about this. So why start a new project? Well, I mean, I needed a new hobby. So I've been working for Nouveau for years, and in the past, well, about 4 years, I've been working for Intel Graphics CI. Well, Nouveau was a very good way to learn about reverse engineering, and I mean, NVIDIA has pretty elegant hardware designs, so that was quite nice. And it teaches about hardware and how to think from a hardware engineer point of view. Then Intel Graphics CI taught me quite a bit about quality and how hardware designs impact quality. What might be like, oh yeah, that's simple, and you know that can work very nicely, can turn out being an integration disaster later on. This is nothing that is Intel specific, but this is something that I've seen there because I've been working at Intel. And then also working with the Intel display driver team, this motivated me to make my own because, you know, how hard could it be? And then, of course, I'm sure there's going to be plenty of issues, but, you know, I just want to learn. And I mean, funnily, Ben Widowski also called for an open GPU last year. At first, I was like, I mean, why now? We've been talking about GPUs using FPGAs forever. And where are they now? So why now would be a good idea? Well, let's go through that. So, I mean, strictly speaking, like, what is left to be done in the open source world? Drivers are nowadays pretty much production ready, and I'm talking about GPU drivers, which were probably the worst for quite a while. So this is really good that we are now to this level. Of course, there's a lot to be done. There's a lot of CI to be done to maintain this production readiness, and there's plenty of things on this field. But other than this, well, are we done? Are we gonna finish there? No, of course not. We need to go further and design our own hardware that we can modify it in the same way that we modify source code. So, is there anything that has changed in the FPGA world that would make it more interesting now? Well, of course, the hardware capabilities keep getting better, and well, I mean, as a tongue-in-cheek, I put that we can implement 10 years old hardware nowadays in FPGAs. Sounds about right. Probably can do much better too, but generally, like, the level of expectations that we could have is this. And so let's say that 1080p frame buffers is definitely achievable, and even more. And also, the most interesting thing for me is that the languages and the workflows have evolved. We can now have open source flows all the way through, and that means you take open source code, you generate the bit stream, which is what is being stored in the FPGA to configure it. And basically, all of this is done using open source software. I just thought that I didn't say what an FPGA was. I'm sorry about this. This is reprogrammable hardware. If you want more information, I strongly suggest you look at Ben Widowski's presentation from last year. And these FPGAs used to be configured using Verilog or using systemc or languages like this, which are not the best. I mean, they are pretty hostile. It's not as bad as writing assembly, but it's a bit like writing C. You're shooting yourself in the foot quite easily. And this is even more so that you have multiple clock domains everywhere, and synchronization, and after some time, you know, people just agree that, hey, this way of working is the best. And then if the language doesn't evolve to make this let's say the proper way being easy to do, then you keep shooting yourself in the foot forever and ever, like memory issues on C. So that is better. And then there's also a lot of powerful IPs that are now available. And of course, the powerful IPs or the hardware blocks are also coming from the fact that the FPGAs themselves are more powerful. Sorry. So how does it look an FPGA? Well, if you want to see a very simple one, this one is the Icebreaker, which is basically like an Arduino but with FPGA inside, so you can do it's the same type of devices that you would be able to make, except this would be much faster. And if you want to make your own display controller, then that would be already sufficient for CATC, for VGA or things like this. But of course, if you want to go with HDMI, that doesn't really work. But then you have also this type of beast, which is PCI Express based with I think it was 8 gigs of HBM2 memory with half a terabit per second bandwidth. Well, a pretty big fan, one must say, and transceivers that can go like to hundreds of gigabit per second. So pretty good stuff. And yeah, sure, you can make some wonderful 8K outputs with that. You don't have to spend the $3,000 that this is on the market, like used on eBay, but that's definitely a possibility. So yeah, the FPGAs are now ranging from 1,000 of LUTs, which is the basic unit for logic, to over 1 million. But on top of this, there's fixed functions that are integrated in these FPGAs. So of course you can just have an ARM CPU there. That's pretty practical. But you can also have, so as I was saying, these the link speeds, the hundreds of gigabit per second. It's basically because there is this fixed function block that takes a parallel bus as an input and then outputs it as a single serial connection. So you can imagine that using this with a memory controller is pretty darn efficient. That works very well. Same for HDMI or DP, and you can actually get to 8K using them. So it's pretty good stuff. Then you can have DSPs, which are basically mad blocks, and you can have multiple tera operations per second. So in integer, like 8-bit integer, of course, but still, you know, it's pretty decent stuff. There's memory controllers, DDR or HBM, although this one is not really a fixed function. PCI Express controller, so you don't have to do it yourself, and you know, things like this. So now that we spoke about the FPGA, then what about this workflow to generate to take the language, the hardware description language, and convert it into well, the bit stream, which is the configuration for the hardware. We have the project called SymbiFlow, which is aiming to be the GCC of FPGAs or the Mesa of FPGAs. And so here is the matrix that is of what is supported, and you can see that there's basically 3 FPGAs that are fully supported. There's the ICE40, the ECP5 from Lattice, all of this done through reverse engineering. QuickLogic, which is not the biggest manufacturer of FPGA, decided to just provide all the documentation that is needed for implementing MBflow, and I think they've been contributing themselves, so pretty good. We've got an open, a vendor-supported open source, not driver, but like not compiler either, but call it whatever you want. And then Xilinx is the leader on the market. It's a bit like NVIDIA for graphics. And the project X-Ray is doing reverse engineering, and things are working pretty well. I mean, they're working so well that I'm getting ahead of myself. I'm sorry. So that's SymbiFlow, which is basically just compiling, but then to generate the code that is used as an input, which is usually Verilog, you can write some higher level code, and one of them, one hardware description language, is called MiGen, and this is Python based. It's very, very nice way of writing blocks, because Python is really well suited to create templates of IP blocks and then configuration of these IP blocks. So it's pretty practical. I'm going to type check. Okay. With this language, MiGen, there's been a project called LiteX that is basically a library of hardware blocks which can be mixed and matched, and these blocks are connected or exposed to anything through a bus, and the bus is wishbone bus. So basically what it allows you to do is you create these blocks, you put them on the bus. They're going to be at separate addresses, and then you can expose these bus through PCI Express, through Ethernet, through UART, whatever works for you. And if you are wondering what can be done, I'm not sure if it's really readable, so I'm going to read it for you. So there's a DRAM controller with over 20 gigabit per second bandwidth, so pretty decent. Yeah, what they're showing is DDR3 connected. There's Light PCI Express block, which supports PCI Express Gen 2 with 4 lanes. You've got DMA engines to enable DMA. And really, if you want to instantiate one DMA controller, it's 2 lines of code. That's it. So it's very nice. Then, as I was talking about, there was the wishbone bus and then wishbone bridge. So here the bridge is connecting PCI Express to wishbone, and it exposes the bus through bar 0. Then you've got an Ethernet controller. You've got a UART controller, SD card, serial. XADC is Xilinx analog to digital converter, which also exposes some values like the temperature or the voltage of the different buses that are there. You can access flash memory using SPI block that is there. You have LiteScope, which is a block that enables, well, in a sense, it's a bit like you would have for performance counters, but this time it's more for debugging, so it's even lower level than JTAG. And you've got HDMI input and output that supports full HD at 60 Hz, and that can definitely be improved to support higher resolutions, but right now it's a pretty old version of HDMI that is implemented. But again, like most users would already be fine with this. So LiteX and SymbiFlow put together, well, you can create a device using one line of code that has well, the DRAM for your device. So let's say like half a gig. And then you have a quad-core RISC-V CPU that is running Linux at 100 megahertz. So this is something that doesn't exist in hardware, but then you can already play with this using an FPGA. It's pretty cool. Then if you want to know what boards exist, so on this front of the ecosystem, there's more and more boards that pop up, mostly thanks to SymbiFlow making dealing with FPGAs much better or much easier. So this one is not out yet. It's the ULX3S. As you can see, it has pretty much everything you might want for a handheld console. HDMI output, a jack, 2 USB outputs, or 2 USBs, micro SD, there's Wi-Fi, there's Bluetooth, there's buttons directly, there's SDRAM, and as a matter of fact, people have been already using this to emulate, I think it was a 286 Intel platform, and then running DOS on this, and so you could run DOS games on this, and that's properly emulated. And there are already emulators like this for a lot of consoles, so you can buy this device, and then if you want to play, I don't know, old games that run exactly at the same clock, no emulation, no, well, it is in a sense, it's hardware emulation, but basically, like, it's perfect. You can't beat that, and yeah, and then you can switch to Game Boy, you can switch to newer stuff. Of course, things have to be written first, but there are already some existing things that prove that it can be done. Then there is the NETV2, which is not exactly new, but it's a very cool device. So it's Xilinx based as opposed to the other one, which was Lattice. So this one is not completely fully supported yet by SymbiFlow. So this is a device that I have, and this is what I'm trying to make the project run on. And this one has PCI Express and there's basically 2 HDMI inputs and 2 HDMI outputs, and this is what I'm trying to use for making my own play controller. I'm going to talk to you about this. So what's missing about this entire ecosystem? Well, one of them is upstream Linux drivers. So you can make an SoC in 10 minutes using LaTeX, but then you'll have to write your own driver for it, which is not exactly cool. And there is work going on the LaTeX work, which is a LaTeX world that is basically using the device tree to expose the addresses of the different blocks. But I would working on making this discovery straight on the bus, which means that no matter how you access the bus, so let's say you run a soft CPU or you run on PCI Express or USB, you would have the same driver for everything, and this driver would instantiate other drivers with the right parameter. So in any case, it's what I'm working on. So the current state of it is that I'm iterating on more effective ways of getting this discoverability done without using too many gates on the FPGA, and also having the cleanest driver possible. And so far, it's pretty good. I mean, the discoverability is like 200 lines of codes or something like this. It's really not bad. I've been really caring about quality from the beginning. So for testing, I do hardware unit tests for all the blocks that I have. Not complete yet, but that's what I'm doing. For driver, I have unit tests with CMOCA, and in the end, I'm going to do integration testing with QEMU and running my design using VeriLater, which is a simulator of hardware, and connect this device, this PCI Express device, to QEMU to expose it to Linux, and then run basically the entire stack in simulation. That needs to be done. The others have done, but not that. So the current blocks that I have, well, the first one is boring. It's just text saying, hey, the author is this person, and then the name of the device is that. Okay. Then there is a way to expose sensors. So any kind of sensor, which is interesting because the driver doesn't know what device it's gonna be running on. So the device itself has to tell everything about what it exposes and how to interpret the value. So it tells you the unit, the calibration function, and it allows you to read a 16-bit value and then say, well, that means it's 16 degrees or it's 80, and then it also exposes the limits for these values. So in HW-MUN, you can see if the value that you see is actually good or not. And this is done in without having any hard-coded values. That's pretty cool. And of course, because I was working so much on for Nouveau on power management, I implemented my own fan controller with a tachometer for the fan speed. That was a cool project, and yeah, so it's pretty cool. It's not merged yet in master, so if you want to see it, you can go to the fan work in progress branch. Okay, so when can we expect a full GPU? Well, let's be realistic. That's really not the first thing we need to do. First thing would be to expose the current LiteX blocks, and then my objective, as I was saying before, is to create a USB/PCI Express display controller and have the same code generate bitstream for 2 different boards and FPGA manufacturers. So that would be lovely. The ETA was, well, let's do this by XDC, which was not a crazy target, but then life came in the way. Of course, the pandemic was a way to get more time, but then with my girlfriend decided to buy a house, get a dog, and I think you get the feel of how things go. And I've been interacting more with the LiteX community, and that led to a lot of redesigns of the core, and so that slowed me down. And of course, XDC, the organization of XDC has been taking some time. Okay, so I'm already over time, but maybe there is one question or two that I could select. So Radek was asking about Intel and Altera. Right now, there's basically no reverse engineering efforts on this front, so that's why it's not mentioned. And Adrian is talking about the DE10 Nano, but I don't know what it is. Okay, well, thanks a lot for your attention, and I'm going to switch back to Arek, and Luke is going to be presenting in 6 minutes the Libre-SOC project, which I guess is anyway much closer to the GPU, open GPU than the LiteDIP is right now. Thank you.
Okay, so we are going to play this pre-recorded talk by Luke, and then we are going to switch to the person, to him in person to ask him questions. So let's go.
Hello, and welcome to a presentation on the Libre-SOC hybrid 3D CPU and GPU. This is for the XDC 2020 conference. Many thanks for inviting me to participate in this, and also many thanks to NLNet for sponsoring this project, the Libre-SOC project, under their Privacy and Enhanced Trust program. The first thing I think is, why on earth will we make another system on a chip, an SoC, in today's market? Well, given that we've got things like the Intel Management Engine, and AMD has a similar backdoor spine coprocessor in their products, given that Apple found more QA issues in Intel's Skylake recently than Intel found in Intel's Skylake recently, and with the yet more speculative execution things. So it was only just last week there was another set of speculative execution vulnerabilities found. It's becoming just, I feel sort of a duty of responsibility to try and do a alternative processor myself. We're running into where your typical SoC is heavily integrated, and as a result, with the GPU and the VPU being on board, the simplest solution that any average fabless semiconductor company will do, Samsung, Rockchip, or Winner, Texas Instruments, is they will license a proprietary hard macro for the GPU and the VPU, and that comes with proprietary firmware that they have to respect the restrictive secretive NDA on that source code. That's if they have access to it at all. And consequently, you end up with a product that when the developers create a product around that, a game or whatever it is, you end up with opaque driver bugs. And this did actually happen with the Samsung S3C 6410, which had a special proprietary GPU developed by Samsung, where if you called the OpenGL initialization functions in the wrong order, you got a memory corruption and a segfault. And there's no way that you could know that that was going to happen because you didn't have access to the source code and you couldn't debug it. So it had a massive adverse effect on product development cost for the customers producing these products. So the alternative was demonstrated by the Intel and Valve Steam collaboration, which on the 2012 blog post, so they said it was the most productive business meeting they'd ever had. And it required no NDAs, no involvement of other than contacting their immediate managers, no third-party agreements, no lawyers, nothing. They just phoned each other up, got permission from their respective managers, and went off to have a business meeting. And consequently, both of them got huge improvements in their respective code bases. Both the Intel driver team and the Valve Steam team massively increased the productivity in their own code bases. So, I'm trying to emphasize here the impact that proprietary development has. It's not a good thing. It has a huge real effect on businesses. The other reason why I'm on a system on a chip, because for 30 years I always wanted to develop inside a CPU. But ultimately, this is a strategic business objective to develop entirely Libre hardware, firmware, and drivers. So why we're using OpenPower, but why? When you're considering doing your own instruction set, your own processor, you need to be realistic about it, and you need to think in terms of, when I present this to customers, are they going to accept it? Are they going to like it? And if there's no ecosystem surrounding your chip, then not only have you shot yourself in the foot as far as presenting yourself with a 20+ man-year development cost. At the end of that, none of your customers are going to buy it because there's no buy-in, there's no Linux kernel, there's no other customers are using it, and there's no ecosystem. So you need Linux kernel, U-boot, compilers, and operating systems, and reference implementations to already exist. You need the support of a founder foundation and the members in that foundation. In particular, what we're intending to do is to submit augmentations to instruction set, and those need to be done properly by probably peer-reviewed by the members and by the foundation. So that you need to support a foundation of members. Because we're funded by NLNet under their Privacy and Enhanced Trust program, there has to be no NDAs, and full transparency has to be acceptable. So no secretive working groups, no closed mailing lists, etc., etc. And the Open Power Foundation have demonstrated that they're amenable to that. They're extremely approachable and friendly. But it also has the advantage that the power instruction set has been established for over 2 decades. And we have Microwatts as a reference platform, which proved extraordinarily valuable. The people behind it, the team behind it, are so knowledgeable. I mean, it's a privilege to work with them. So what goes into a typical SoC? Normally will have a fully integrated set of peripherals. It is not a Northbridge, Southbridge design, which you typically see in an Intel processor, and it's nothing like the IBM Power 9 and Power 10 core, where you have high-performance I/O and PCI Express, and not really very much else. Your typical system on a chip will go on, including the power management chip and the memory chip, which will be a 3D stacked DRAM and NAND flash on top. Your typical PCB size is 30 millimeters by 40 millimeters. Let that sink in. It's normally the size that's smaller than your average Intel BGA processor, and definitely smaller than your average your IBM Power Core. All right, so the entire package is fit between 15 to 20 millimeters BGA. Power consumption is 2.5 to 5 watt power consumption, which means that you can use a plastic FPGA package. You don't even need a metal top on it, and you don't need a heatsink. This overall simplifies the design drastically and cuts down the cost on development for the PCBs and product development for for your customers. So you have things like USB 2, USB 3, HDMI, RGB-TTL, MIPI, micro SD, lots of these, lots of I2Cs, lots of UARTs, full and partial, lots of SPIs, including quad, you have GPIO, external interrupts, PWM, audio built in typically, although it's usually AC97 compliant I2S for connection to external Maxim chips, etc., and Akai audio chips, although some will actually have analog A to D converters on board with headphone and line in, line out, etc., because those chips, those audio chips will typically be about sometime between $1 and $3, and the actual processor is selling for between $2.50 and $4, or sometimes up to $30, but it depends on the market. So, for example, the Freescale quad-core IMX6 sells for $35, whereas the Ingenic JZ4775 is at the $2.50 mark. So it is a completely different kind of market from your average Intel processor, AMD processor, or IBM Power 9 or Power 10 core. And there's also a built-in GPU and built-in CPU on a shared memory bus. It doesn't even have separate memory lines for the GPU. It's internally a shared bus architecture. So this is what you'd typically see inside your simple single board computer style Raspberry Pi. I don't like the term, but it's your credit card size computer board. The processor would obviously take up about 1% or 5% of the space on that board. Memory would take up another 10%. Power management about a third of the board. So you'd have video processing. Instructions and 3D instructions actually built into the core. All right. So we are doing an Open Power out of order instruction set multi-issue, where the simple vector extension, which I'll explain later on, is part of that thing, but it's actually part of the augmentation of the power instruction set, which we will need to get approval from Open Power Foundation before we can release it. We have to go through a proper process with this. Then you'd have that core will be connected to Axie4 wishbone buses and bridges, etc., and then you would have your peripherals and your memory. Now, here, this pin set, as you can see with many of the Texas Instruments and Samsung things, if you've read the technical manuals, you'll find that there's like 1,500 pins of actual functions, but the actual number of pins is way smaller of that, because if you have a 1,000 pin package, you end up with it's just too big and it's too costly, and the yields are much lower on the larger packages. So what you do instead is you have this pinmux, which takes those 1,000 pins and multiplexes them down to, say, 200, 250, or 150 external I/O pins. And then in software, in the GPIO, in the kernel, in UBoot, you set which of those functions you want to be. So you want pin A5 to be I2C clock, or you want it to be on somebody else, another customer would set that to be UART transmit, UART 0 TX. And that's all software programmable at kernel level, or in embedded operating system. And in this way, you can design a chip which has multiple markets and multiple potential target markets. So one chip, 15 different customers or customer markets, which then increases the probability that your chip is actually going to be successful because you're not critically dependent on one customer only. So what's specifically different about Libre-SOC? Well, the first thing is, the most critically important thing is that it's a hybrid integrated CPU, GPU, VPU. The CPU is the GPU is the CPU, and likewise for the VPU. So there is no separate VPU, GPU, pipeline, or core. We are actually augmenting the power instruction set to add vectorization suitable for 3D GPU and VPU usage, and then augmenting the instruction set itself to add targeted instructions for those specific purposes. I apologize, I have to emphasize that because it takes quite a long time for getting across to people, and I've talked about it, and then 6 months later they've gone, so you're doing a separate GPU, are you? It's like, no, I'm not, we're not. I'll explain. I'll go over the other points and then come back to that and explain why that's significant. Thing. The second thing is that it's written in Namibian, which is a Python-based HDL. We did several weeks of comprehensive analysis of alternative HDLs. So it's not VHDL, it is not Verilog, and it's definitely not Chisel 3 or Scala. This is actually extremely important strategic decision, which we'll go into a bit later. But Verilog is designed from the 1980s. It was actually designed for test purposes, for unit tests. It was only after it had been designed for unit tests that somebody noticed that actually you could write the HDL itself in Verilog as well. And that's how it took off. VHDL is much more gate-level design, but it has the advantage that it can include records. But ultimately, and this is one of the reasons why Chisel was done, is you cannot do object-oriented programming on top of Verilog or VHDL. They are 1980s basic and Fortran style programming languages that have not evolved as the rest of software engineering software development practices have get up. Chisel is just, you take one look at it. I've done dozens of programming languages and I still cannot read Chisel. I didn't learn Java. I looked at it and I can read it. That's one of the reasons why Java became so popular. And Python likewise became popular because it's readable by humans. Chisel is just, it isn't. So despite the fact that it has these object-oriented capabilities, it's unusable. So we need the object-oriented capabilities, and Python was the most obvious choice to pick. The other thing that's different is that we're using our own vector extension, which is called SimpleV. And you have to have a look at an article online on SIGARCH, which you can find with SIMD considered harmful, and it explains emphasizes that the setup and teardown costs of SIMD are so insane that it's just why we're doing this. And I'll show an example later on. But ultimately, SimpleV is like a hardware for loop on a standard scalar instruction set. So if you can think in terms of pausing the program counter, then doing a sub-counter loop from 0 to the vector length, incrementing the scalar register numbers by 1 each time, you get the general idea. And conceptually, it's very similar to zero overhead loops in DSPs. So just coming back to the thing about the hybrid GPU. I apologize, I've forgotten what it was I was going to say. That's moving swiftly on. So we have we're basing it on a hybrid architecture using an augmented CDC 6600 as the inspiration. So whilst the CDC 600 itself is designed from 1965, the augmentations that we are putting on top of it are not. So with help from Mitch Alsop on comp.arch, who spent 6 months very kindly explaining to me how the 6600s and scoreboard systems work, we're adding precise exceptions, multi-issue, and much more. So the academic literature on the 6600 is completely misleading. I'm not kidding. I've had to do a comprehensive article explaining how to morph the Tomasulo algorithm, which is the one that is believed in the academic literature to be the canonical way of doing out of order. I've had to write an article explaining to people how to morph that, topologically morph that into 6600, preserving all of the capabilities of the Tomasulo algorithm, but without the overhead of the cost of the CAMs and the disadvantages of using binary addressing. That article, if anybody's interested, I can point you at it. But basically, it comes down to the fact that Seymour Cray, because they were so early, they solved problems that they didn't realize actually existed elsewhere. And consequently, what they didn't do in the literature or in the patent is actually highlight the fact that they'd created register renaming, because they didn't realize that register naming was a problem. They just solved it. It's kind of ironic that it's taken 50 years for this to come to light. So we're putting on the Cray-style vector front end on the instruction set, but at the back end, we're doing predicated masked SIMD. So there's this little interpreter loop in the instruction decoder, which sits between the instruction decode and issue, which effectively does that for loop, throwing out multiple instructions into the multi-issue engine, some of which are going to be SIMDified, that give us the appearance of having vector front end, but without all of the disadvantages that come with a SIMD instruction set. So this out of order execution combined with multi-issue, combined with simple V, allows a developer to think in scalar operations, but they're turned into SIMD at the back end without the developer actually needing to do SIMD, and that poisoning the entire code base with these set up and tear down code fragments. And then on top of that, what we were doing is adding IEEE 754 sine, cosine, atan2, log1p, normalization opcodes, texturization, which texturization in 3D GPUs, you have 4 XY. You have 4 values representing 0, 0, 0, 1, 1, 0, and 1, 1 on a 2-dimensional grid. And then you have 2 parameters x and y from 0 to 1, which you interpolate the 4 points for the texture things, and you get a graded pixel value back. So it's particularly complex interpolation involved, which we've got to add as hardware, because if we don't add it as hardware, we're going to end up not being sufficiently high pixel per clock rate to be commercially viable. And then we'll be also adding YUV to RGB, which could be used for both the video decode and for audio, potentially, if we get the encoding right, but also for the 3D pixelation as well. And thanks to Simple V, we only have to develop these as in scalar form, and it will be automatically vectorized by the Simple V extension. So why the heck are we using Namegen? I mean, any other team would go, oh, we'll use scalar, we'll use VHDL, or whatever it is. Now, Namegen uses Python to build an abstract syntax tree in memory, which then hands that over to Yosis for blind creation of ilang files, and you then use Yosis to do turn it into Verilog if you want, and hand it over to standard synthesis tools, or you can put it straight into free software tools. For example, we're using the Versa ECP5 for FPGA, using Next PNR. We don't have any proprietary tools in this at all, so it's part of the free software toolchain. But ultimately, we can use Python object-oriented programming techniques in everything. So, come through the slides here. We get deterministic synthesizable behavior. So in Namegen, signals are declared with their reset pattern, so there's no more forgetting the if reset block in your VHDL or your Verilog, because it's back in the declaration of the signal, and Namegen automatically creates the if reset for you behind the scenes on your behalf. And if you forget to add it, it defaults to 0. So a huge number of the problems associated with Verilog and VHDL just go away. So again, we can use Python object-oriented programming techniques. So we can use standard Python classes and functions, which you can pass in parameters completely depends on what the type of HDL is created. And in this way, we've created an IEEE 754 floating point pipeline library, where the size of the IEEE floating point, whether it's FP 16, 32, 64, is just a parameter. Right. It's exactly the same code, and this drastically reduces the amount of code that we then have to maintain. We don't have a separate floating point pipeline. We don't have a separate 32-bit pipeline, 64, and a separate 80-bit and a second 128-bit one. It's all the same code. Right. A software engineer would think of this, but a hardware engineer would not. Right, because they're restricting their mindset to HDL and thinking in terms of, I have to write the code by hand, and thing. So we can also apply Python-based for loops to, say, for example, read the CSV file and iterate over that in Python and generate the abstract syntax tree to create a hierarchical recursive nested suite of HDL switch and case statements. And that's how we've implemented the Libre-SOC power instruction set decoder, power ISET decoder. In the more extreme case, we're actually using object-OA abstraction. I don't know if you're familiar with the overloading of underscore, add, underscore in Python, etc. In the similar things for subtract and add and greater than, etc. You can create your own class where if you do A plus B, X equals A plus B, under the scenes, behind the scenes, Python will call X equals A dot underscore add underscore brackets B on your behalf. So you can think in terms of a simple thing of, I'm adding A to B, but underneath, just like in C++ operator overloading, you're doing something completely different. And so what we're using that to do is to do these dynamic partition signals where there is a context associated with it, which breaks the signal down, the 64-bit signal, down into 32, 2 times 32, 4 times 16, or 8 times 64. And so we can have dynamic partition SIMD, but still looks like we're doing X equals A plus B. Right? And as a result, we don't have this insane switch statement in the top level of code, expanding every single statement into a massive series of suite of switch statements, or having multiple identical versions of the exact same code, one for 8-bit SIMD, one for 16-bit SIMD, one for 32, and finally one for 64-bit in Scalar. It's literally going to be the same code with this abstraction on top. I don't understand why this hasn't been thought of before when you're in an industry standard practice. So why are we doing another vector instruction set? Well, SIMD, strictly speaking, is not another SIMD instruction set. It's a register tagging system, and consequently there are no opcodes, additional opcodes. There is no floating point 16 add. There is only scalar add with the vector hardware for loop hidden behind the scenes. So we're tagging scalar operations operating on the scalar reg file as vectorized. Now, the consequence for this is that we can completely discard the power instruction set SIMD, which is 700 opcodes. And to give you some idea, we've implemented the same instruction set as micro at the moment, which is the integer things, and that's 300 instructions. Floating point adds about another 100 to 150. And then when you implement VSX, it's a whopping 700 additional opcodes. And this is pretty normal for SIMD. All right, but it makes it extremely unlikely for us to be able to fit a power instruction set decoder into only one clock cycle. Already, without us having added in the floating point scalar instructions, we're at 4,000 gates for the power ISA decoder, which is larger than some RISC processors. Okay, so we really don't want to do power SIMD. So, as I said, it's effectively a hardware sub-counter for loop, which pauses the program counter and then incrementally rolls through the operand register numbers, distributing multiple scalar instructions into the pipelines. And this is the reason why we're doing we're doing this on top of a multi-issue out-of-order microarchitecture, because we can shove these multiple scalar instructions into those pipelines, and this out-of-order engine will take care of it. We also did another advantage of Simple V is that current and future power instruction scalar opcodes inherently and automatically become vectorized by Simple V without needing a new explicit new vector opcode, because it's automatic. even predication and element width polymorphism are also tags. So the element width polymorphism allows us to have floating points 16 and 80 and 128 without modifying, added to the instruction set, the power ISO instruction set, without modifying the power instruction set. Because you just say, well, this 64-bit floating point add operation for the duration of this operation, instead we're going to do floating point 16. It's real simple. So just to give you a quick refresher on SIMD, it's very, very easy to implement in hardware, and consequently is extremely seductive. The parallelism is in the ALU. It's not in the instruction decode or anything like that. So there's zero to negligible impact on the rest of the core. All right. But where it goes wrong, as illustrated in that SIMD consider harmful thing, is the setup and corner cases make it extremely complex. So the hardware is easy, but the software is absolute hell. Right, and this applies to 3D GPUs just as much. Right, and I've just encountered a Stringer copy patch to Power 9, which was added last month. It's 250 handwritten lines of assembly code. And for RISC-V RVV and for Simple V, which are based on the Cray vector length concept, Stringer copy is 14 instructions. Let that sink in for a moment. Right, 250 handwritten assembly lines versus 14. All right. The other thing is that you actually have an order n to the 6 opcode proliferation, which results in thousands of instructions. So you have the opcode itself, so whether it's an add, a multiply, or et cetera. You have the element width, so you have whether that's an add, a 16-bit, an 8-bit, 32 or 64. You have the vector length, which in now Intel has gone up to 512-bit vector AVX. I mean, it's mental. You have whether the source 1 or the source 2 and the destination are scalar or vector, and all the permutations of those. All right, and you have some cases where you want to select the high or the low bit of the result. So this is typically done in 16-bit audio processing. When you do the multiply, you want to select the high result of the multiply rather than the low, and you consequently have these permutations of things. It's 4 permutations of what you can have of whether you want to it's ridiculous. And then you have the selection between the scalar file. You have copy instructions, move to and from scalar to register, scalar to vector, vector to scalar, scalar to predicate, predicate to scalar, predicate to vector, vector to predicate. It's mental, and we can avoid all of it with this register tagging system. So just to illustrate that Simple V in a nutshell thing, note that this is the add instruction. It's a scalar add instruction, not a vector add. It just happens to have been augmented. The scalar add has been augmented so that if the registers are tagged as vectorized, it automatically goes into this vector loop. So normally what you would do is you would have, for scalar operation, VL would be set to 1, right, so that you would only have 1 instruction issued into the execution engine, and predication would be disabled. Right. However, should you enable VL, vector length set it to 4, 8, or even 7 or 19, then it goes into this hardware for loop where on the first iteration you get what we would expect to be your standard scalar instruction. But on the second loop, it goes, if the destination register is vectorized, then increment the destination register number which is used there. And if the first source operand is vectorized, then increment that and add it onto this register number. All right, and the second operand likewise. So you can inherently you can see that for a very, very simple implementation, which there's virtually no impact on the amount of hardware that's required, you simply have to add this counter, just a sub-program counter, shoving instructions, going around shoving extra instructions into the issue engine, and it becomes extremely simple to conceptually and in hardware and also in the cycle active simulators to add this for loop in to create a simple version of the simple compliant implementation. It gets more complex when you want to parallelize that, but this is why we're doing the out of order engine, because we just shove it at the thing and the out of order engine goes and sorts out the parallelism for us. I left out register indirection and a whole stack of other things, but also I left out element width overrides, which I'll cover later. So your scalar vector, and vector vector are now all combined into the same instruction. You haven't had to add a scalar vector SIMD instruction or a vector vector thing. It's the same. It's scalar add. Right. So again, out of order may choose to push their adds into instruction queue, which makes it very busy, and consequently, you have an extremely compact way to express instructions, and that in turn saves you on instruction cache and saves power. All right. So another example here is we're overloading the meaning of what a branch instruction is by turning it into predication. All right. So instead of the first thing you do is you check to see whether the registers are vectorized. All right. And if they're scalar, then you jump to the branch or conditionally or whatever it is you're doing in your normal branch operation. But if it's not, then you do not do a branch. Instead, you treat it as a predication, an opportunity to calculate a predicate using the source 1 and the source 2 for your registers for your branch to do a compare, all right, and to store the result in a predicate register. All right, so we're kind of changing the meaning of what a branch is, but we're doing it through the tagging. So if the registers are tagged as vectorized, then it does the predicated form. Otherwise, it behaves exactly like a scalar branch. All right. So predication is stored in the integer register file as a bit field. We have scalar vector and vector vector predicate computation supported. But also we aim to overload the branch immediate to be the predication target. It's complicated, it's a thing, but I wanted to give you the sort of a high-level overview of what we're thinking. Details are in the actual implementation. So the other thing that we're doing is similar to MMX, but done slightly better. And to Power9 VSX in some of the low power simpler versions. So we're actually typecasting the register files with a union. All right, so we sort of treat the register file as if it was a byte level SRAM. All right, where again, I apologize, this is C pseudocode. So we have 128 registers which are of type reg_t, where for in most intents purpose, it looks like it's a 64 bits, 8 bit actual bytes. But the addition is this union here, where we can override the element width with a tag on the register to say that actually I know you're doing this is nominally a 64-bit add, but actually I want you to treat register A as a SIMD array of 8-bit things starting at the point in the register file, which is normally associated with that 64-bit scalar register. Implementation-wise, this requires us to have byte-level select lines on the internal SRAM, which, given that Wishbone, it's exactly what Wishbone does. You have can have up to a byte-level granularity on these select lines. It's no skin off our nose to do this in terms of hardware. The only thing is that for 64-bit scalar writes, you have to enable all 8 select lines to get at the 64-bit data because it's byte-level selects. So the default behavior is that your elements, they're not elements, but you know what I mean, your elements behave as defined by the standard instruction set. And for integer operands, there's an override which turns it into 8, 16, or 32-bit SIMD. So for 8-bit, it would use that. For 16-bit, it would use that. For 32-bit, it would use that. And when it's default and SIMD default width, it would use that. So it's as if you had that array, which comes back to basically doing this. All right. So it typecasts the register file to this union of arrays. And for floating point, IEEE 754 floating point, we can add floating point 16 and later 80 or 128-bit without adding actual floating point 16 instructions to the instruction set. consequently, this drastically simplifies and keeps the decoder simple, and consequently, we reduce the power and standard chance of actually being able to do the instruction decode, power instruction decode in a single clock cycle. So all of these things have to be taken into consideration in this design. So again, it does not require modification of the actual ISA. Conceptually, I don't know if you're familiar with the mill architecture, but it's exactly the same thing. So the mill architecture, they don't even have floating point add 16 or int add 16 or floating point add 32 or 64 or int 32 or 64 add. It's just add. All right, and the tag of what the type of the register is taken from the load instruction. So you specify at the load instruction whether it is 8, 16, 32 or 64 bit. You specify at the load instruction whether it is integer or floating point or complex numbers or bit. Actually, they can actually do bit level addition. It's really well worth looking up if you're interested in architectures. And that tag goes right the way through until you do the store. It's a fascinating design, and consequently, the instruction set is extremely compact because there is no floating point add, no 16-bit add. There's just add and multiply. So we can't do that because we're at extreme level because we're working on top of an existing instruction set. But at least what we can do is say that the floating point add 64, we can tag it to say, actually, I want you to do floating point 16 add or an array, a SIMD array of floating point 16s, please, but without having to add an FP add 16 opcode. That's really important. So now one other thing to say is that when the vector length is say 3 or 12 and the element is 16, normally that would take up only 48 bits of the VL equals 3 and L equals 16. That would take up only 48 bits of a 64-bit register. What we do not do is 0 the upper 16 bits. They are untouched. All right. So regfile ra.s, s being the 16T thing here in that union, that is not zeroed, is not touched, and in the hardware it means that bits 6 and 7 of the select lines are disabled, and those go directly to the predicate line. So inherently the predicate bits at the top, which are not touched by the VL, are left at 0. Some additional features on nSimple-V include fail on first. Fail on first is something that is extremely significant, has been discovered to be extremely significant, and has been added to ARM's SVE and SVE2. Basically, if you have a look at you can find the patch on the glibc mailing list for Power9 VSX Stringer copy. When you get to the top of the page boundary of the memory of that you're doing, VSX is 16 bytes. And if you start the Stringer copy within 15 bytes of the end of the page, you will automatically get a segfault. And consequently, the very well-written assembly code, 250 lines of it, completely fails to when you try to use this strict copy assembly routine at the top limit of the memory. So what fail on first does, and this can only really be done when you have predication, which Power9 does not have in its SIMD. You can only do this with predication or vector length. Is you go when the load would fail, what I would like you to do is simply, instead of issuing a segfault, is to simply automatically truncate the predication or the vector length to the last item which will be successfully succeed. And consequently, all other operations in that loop will be truncated and will succeed within the bounds, in parallel, will succeed within that now limited range of operation, including the store. And this is extremely important to have in a vector instruction set. If you don't want to have to do the if, well, it might succeed, might fail, so I'm going to have to put a detection in the loop, and you're wasting instructions. All right. So fail on first does away with the need to do that, and it's extremely important. The other thing, which is something which is accidentally added is something called twin predication. And on things like move instruction between two registers, we're applying a predicate to the source register and a completely separate predicate to the destination register. And in combination with setting one of those to scalar and one of them to vector, or both to vector and vector, this combination covers all of the traditional vector operations: vsplat, vgather, scatter, index, etc., reduce, etc. All of them are covered by twin predication. So again, we don't have to add vgather, vsplat, flat, etc., because it's to the instruction set, because it's already covered. So the other thing that we're doing is we're doing this what's called SV prefix, which is embedded by Jacob. Jacob is one of our team members, and it's a 16-bit and 32-bit prefix on the scalar operations, which turn the 32-bit operation into a vector operation. SVP64, obviously having many more bits, allows for a much more extensive tag augmentation of the scalar instructions than the 16-bit prefix does, which is SVP48. The other one is, which is much more advanced and is still in development, is vblock, which is sort of like VLIW, and it's a context which allows space for 3D operand swizzle and things like that to be tags in the things. And ultimately, what we're doing is it's a hardware compression algorithm for instruction sets. The ultimate goal being to cut on instruction cache usage and therefore cutting down on power. It's actually really significant because I'm not sure if you're aware, but if you were to, this happened with ARM64, is that the increase in the register sizes and the data sizes automatically inherently increased the instruction size to the point where they had a 10% increase in power consumption for the exact same code compiled for the alternative operating system, because the code no longer fitted into a 32K or 64K cache, and consequently, to get the same level of performance, ARM had to recommend that everybody increase their caches by 50%. And that 50% increase in cache size actually results in a 100% increase in power consumption. Right? It's really significant. So, and for a typical GPU which has its own instruction cache and very small shaders, there's no problem. You can have 128 VLIW because those 128 4 32-bit instructions operating in parallel do 4 floating point operations each, where you're getting 16 floating point operations for a 128-bit instruction set. That's a fantastic value for money, but for us, it has a massive impact. 128-bit instructions would have a massive impact on the workload for these scalar operations, because it's a shared instruction cache, which is a hybrid CPU. There is no separate GPU iCache, and so consequently, we really need to have to pay attention to these kinds of things. And it's real architecture design is really, you have to do a hell of a lot of comprehensive considerations. It's really complex, but critically, all of these things need to go through Open Power Foundation for official approval. So a summary then is that our goal is to create a mass volume, low power embedded system on a chip suitable for use in netbooks, smartphones, Chromebooks, tablets, smartphones, IoT, single board computers, and blah, blah, blah. Basically, if you're familiar with Raspberry Pi processor, with Allwinner A64, with the ROC chip RK3399, that's our target. Right. There is no way that we could implement a project of this magnitude without using NIM-EGEN, because we're able to compactify the code using Python object OO techniques to create our HDL. Collaboration with the Open Power Foundation and its members is absolutely essential. There are no shortcuts here. The standards have to be developed and ratified by the Open Power Foundation, not just for us, but so that everyone benefits from the augmentations that we're doing. But adding sine and cosine, IEEE 754 sine and cosine, etc. So we'll be, if that made it into Power 11, would be absolutely fantastic, a huge benefit to well beyond just our project and our product. So we're working on the back of the huge stability of the power ecosystem, which is 25 years now ongoing. The the approach that we're taking is to greatly simplify the Open3D NVIDIA drivers, reduce this product development cost for customers, a la Valsteel collaboration showed. And it just happens to be fascinating, deeply rewarding, and technically challenging, and it's funded by NLNet, which is brilliant. So if anybody would like to help and get involved, we actually have funding where you can actually be paid to work on something like this. So that's it. Thank you very much. Any questions? And if there's any discussion, we have a mailman mailing list, list.Libre-SOC.org. We have a Freenode IRC channel, #Libre-SOC. Website is Libre-SOC.org. And if anybody has any ideas or wants to apply for funding for anything to do with privacy and enhanced trust, just go to nlnet.nl's website. Thank you very much.
So that's it for the presentation, and we have Luke here in person. We are already on time, but probably he will be able to answer 1 or 2 questions. And let's start with probably the most common one you hear. So why not RISC-V?
Goodness me. I have to be quite diplomatic here. I spent 18 months attempting to basically, we're funded by NLNet, and we have full transparency as a hard requirement for the full development of our processor. And unfortunately, RISC-V is developed using closed mailing lists and closed working groups. And that is completely incompatible with the transparency requirements for our processor. Imagine that, basically we're developing a secure processor, DRM-free, spyware-free, and we would get questions from our customers saying, "You're developing the instruction set in total secrecy. How in hell's name can we trust you?" And it would be game over. Completely, will be quite rightly accused of total hypocrisy, and so constantly, very sadly, we couldn't do it. But it's tried for 18 months to get them to understand. They just stonewalled and failed to answer absolutely every single time.
Okay, I guess we can squeeze one more. That was really nice answer. So how do you achieve the parallelism needed to run shaders on your CPU/GPU without single instruction multiple data? And does that result perform on par with what it would be if they were SIMD?
Right. So as I mentioned in talk, it's a vector front end, but a SIMD predicated back end. So what SimpleV does is it sits in between the instruction decode phase and the instruction issue phase, doing working out whether the instruction in combination with that VL for loop can issue that 8-bit vector to the SIMD hardware backend. So you get both advantages of the simplification in the assembly level of VL, as I described in that SIMD considered harmful thing, with the Cray vector things. But at the use, as hardware engineers, we can still greatly simplify the design of the hardware by still doing predicated SIMD. But it's just it's not exposed to at the API level, aka the instruction set.
Yeah, thank you very much for your presentation and for your work on OpenSOC, and we will have another presentation soon. Thank you very much.
Thank you.
Hi, I'm Eleni Stea, and I'm working for Italia. I'm going to talk to you about the OpenGL interoperability extensions and our work to support them on different mesa drivers. The aim of the interoperability extensions is to enable the user to allocate the resources that are required for rendering, like textures or buffers, from Vulkan once, and reuse them several times from both APIs from both OpenGL and Vulkan, and synchronize the access of those APIs to these shared resources. An example of an application that would use interoperability is a VR compositor where the left and right eye images would be allocated and displayed by Vulkan, but their contents would be filled by OpenGL processes. Now, the OpenGL interoperability extensions are grouped in two main categories. The first one, that contains the XMemory Object-FD and XSemaphore-FD, enables OpenGL applications to import memory objects or semaphores from POSIX file descriptor external handles. And the second one, the External Objects category, contains the extensions that enable OpenGL applications to create OpenGL objects corresponding to Vulkan ones and synchronize access to shared objects across APIs. It also extends some existing GL calls that set and query properties with new properties. Italia contributed to the implementation of the interoperability extensions for different mesa drivers, but also to Piglit, because there were no conformance tests available for these extensions, and so we've written a Vulkan framework for Piglit and some tests that cover the most common external objects and external objects FD use cases. More specifically, we've implemented the extensions for the Iris driver, and our branch is under review. We've also implemented the feature for FreeTreno, and that work is upstream. And we are currently working on fixes to the Radio SI implementation that were for problems that were revealed after running the Piglit tests, because the feature for because the extensions were already implemented for the AMD driver. And also we helped with the review of the i965 implementation of these extensions that was implemented mainly by Ron Garg here from Collabora. And I'd like to thank all the people who contributed to this work with patches or reviews or comments and advices. I have all the names here because they are too many. And I'd like to particularly thank Tapanipali from Intel, who helped us a lot with his patches and his comments and his reviews on the work for Iris. Now on Piglit, we've covered some possible use cases of these extensions. The first group of tests is about reusing color images, and the most simple use case is the VK image override, where Vulkan allocates images of different formats and tiling modes, then fills them with green, and we expect to see a green screen for each image. Then next test is VK image display, where Vulkan creates an image and fills it with colored bars, this pattern here, and then OpenGL draws the image on screen using semaphores to synchronize access, and the expected output is this stripes pattern on screen. Then next test is VK image display override that also creates an image and fills it with Vulkan, and the pattern that is created from Vulkan is this one. Then OpenGL overrides that image with another stripes pattern, this one, and then Vulkan reads back the contents of the image. We expect to read back the modified contents of the image. Then next group of tests is about depth and stencil buffer exchange. And in the first test, which is the VK depth display, we draw a quad at a specific test to fill the Z buffer with a recognizable pattern from Vulkan. Then we use that Vulkan Z buffer from OpenGL, where we clear the frame buffer to green, and then we render a blue full screen quad positioned on the Z-axis further away than the depth of the original quad. And then if the Z buffer has been imported correctly, the quad is partially obscured due to the depth test failing in the middle, as you can see here, where the all pixels are blue, but in the middle we see the green frame buffer color. Now the VK stencil display is quite similar. The Vulkan creates a pattern in the stencil buffer, and then OpenGL draws a blue full screen quad with the stencil test enabled, and we expect to see the quad masked by the stencil pattern, like here, where the pixels that pass the stencil test are blue, but the rest of the pixels are green, which is again the frame buffer color, the screen frame buffer color. Now, next group of tests is about reusing pixel buffers. In the first test, VK buffer exchange, Vulkan creates and fills an image with color bars and copies each content to a buffer. Then OpenGL uses this Vulkan buffer as pixel storage for a texture and displays it. And we expect to see the striped color bars on screen. Then next test, VK pixbuff update errors, is quite similar to the previous one, but then OpenGL attempts to override the buffer, and we expect an invalid operation error to be generated and the buffer to remain unchanged. Now, the following tests and the final ones are about reusing vertex buffers. The first one, in VK vert buff update errors, Vulkan creates a vertex buffer and fills it with only the odd quads of the HS board pattern, so that not all quads we see contain geometry. And then OpenGL clears the screen to red and draws the vertex buffer in blue. Also, it attempts to override the vertex buffer object. What we expect to see is a red-blue chessboard pattern on screen and an invalid operation error due to the attempt to override the buffer. Now, the VK vert buff reuse is very similar to the previous one, but instead of attempting to override the buffer, we reuse it from Vulkan in a render path that also draws the same chessboard, and we expect to see the chessboard on screen. Many people helped us with the work on the tests and the framework as well. Juan Suarez Romero made some contributions and also helped with the first test cases and did a lot of testing. And then Tapani Pali, who did all the reviews. and a lot of testing as well, and he sent us some patches for the framework. Then is Bas Nieuwhuizen, who sent us a framework patch to support dedicated memory, which is required for the RadioNSI driver, and we didn't support it. Then, and finally, it's Toby Pohjolainen, who had made a first attempt to write tests for this extension some years ago. The tests weren't upstream, but they gave us an idea on how to start, and we had them like a reference for the very first tests we've written. I hope I'm not forgetting anyone here. Thanks to everyone who made contributions. And let's see our conclusions from running the tests. First of all, most of the Piglit tests are passing in the Mesa drivers mentioned before, which is very good. It means that the implementation is probably correct. But unfortunately, Mesa does not support yet the depth and stencil buffer exchange. The only implementation I've found that currently supports this feature is the NVIDIA proprietary driver. No Mesa driver supports it yet. Also, we found some issues with the RadioNSI, but most of them were caused by our changes to the state tracker. And we are working on the rest. I hope that I have the chance to answer questions during the XDC, but in case we just play this recorded presentation, you can email me at this email or ping me on IRC where my nick is Hikiko. Here are some links that might be interesting. The first one is a category in my blog where I'm planning I've started posting and I'm planning to continue posting about the Piglit use cases I've explained before. And these two links are the specifications of the extensions I was talking about. And that was it. Thank you very much for watching and have a nice day or evening. Bye.
Okay, we are now live for questions. So Eleni, you're live. Okay, so
Hi.
There is a question that is, are there plans to support this on Nuvo?
Actually, I haven't checked Nuvo yet. I don't know if it is already implemented or it completely lacks support for the extension. Mm-hmm. So for the moment, there are no plans to support it, but maybe in the future.
Well, Jason Ekstrand was saying we need a Nuvo Vulkan driver first, which is a fair question, a fair statement.
Okay.
Another question is, what Mesa version is targeted for the Iris Freedreno work?
I think that, for the Freedreno, it is upstream, so I suppose the next Mesa version will have it. For the Iris, I don't know, I'm not sure if it will be in the next release or later, because the branch is still under review.
Okay. I think this is the last question, but maybe we can give another 10 seconds or so, the last one. I mean, we are way ahead of time. Okay, then I guess that was the last question. Thank you very much, Eleni.
Thank you very much for watching.
Bye-bye.
Bye.
Jason, the stage is yours.
Hello, everybody. Welcome to my talk about ray tracing in Vulkan. So today I'm going to be giving a brief overview of the provisional VKKHR ray tracing API. So a bit about me. My name is Jason. I work for Intel. I have been around the free desktop community for about 7.5 years now. And I work on basically all of the Intel stuff and lots of shared code bits, mostly around Vulkan. Basically, the only Intel thing I don't do is much work on OpenGL front-end parts. I basically work everywhere else. Not much more to say about that. So bit of background history on ray tracing. So in March of 2018, Microsoft announced the DirectX ray tracing extension, or DXR. And that was followed pretty quickly, about 6 months later, by a Vulkan NVIDIA-specific extension, along with NVIDIA's new Turing GPUs with hardware support for the new DXR feature. A lot of the DXR API appears to be developed, but roughly based on a pre-existing accelerated ray tracing API that was NVIDIA specific, but it came to DXR and then to Vulkan. In March 17th of this year, Kronos released a provisional cross-vendor extension. We've been working on it for a little while before March, but we released it in March. And this contains a Vulkan extension as well as a SPIR-V extension. And the current extension is provisional. That means that it's in progress. It's not actually final. Nobody is shipping it in production drivers yet. Because there might still be some changes that happen between the final version and the provisional. Final version is expected to come out sometime soon. But exact dates are still a bit TBD, and I can't say, but it is coming. So what am I going to talk about? So most of the objective of this presentation is to be educational. I'm going to overview the basic ray tracing concepts, walk through how all of that maps to Vulkan. I'll be focusing on the currently public provisional Vulkan ray tracing extension. Again, it's provisional. Final extension may change a little bit, but the rough shape should be basically the same between the two. I'm not going to talk about any hardware details. I'm not going to talk about any plans Intel may or may not have. I'm entirely focused on the Vulkan API from sort of the Kronos perspective. So to start off, let's talk a little bit about what ray tracing is. Most people here are at least have some level of familiarity with forward rendering because that's what we do on a daily basis, but maybe not ray tracing. So first, in order to understand ray tracing, we need to understand that fundamentally all 3D rendering is a simulation of physical light. So what do I mean by that? Let's say we have this scene. We've got a cowboy, and he's looking out in his field. He's got a cactus and a cow. And how does he see these things? So the way he sees these things is that the sun is emitting light in the form of photons. And these photons fly out from the sun, and they bounce off the objects. And eventually, some of those photons end up in his eyeball. And that's the way that we see things. And we know how this works physically. Light bounces off at the same angle relative to the perpendicular. Roughly, there's some scattering effects, etc. I'm not going to give a physics class, but the basic idea is we have all these photons coming out of the sun that eventually come into our eyeballs. So let's say we want to. Let's say we want to simulate light. Why don't we do 3D rendering this way? The primary problem is there's a huge amount of waste. So if we just took a random photon and emitted it from the sun in a random direction, there's about a 1 in 2 times 10 to the 9th chance that the photon will even hit the Earth. Of those photons that hit the Earth, only about 1 in every 4 times 10 to the 10 will hit a 100-foot radius or 30-meter radius on the planet. So if you're looking at a scene, 100 feet is a reasonable radius for most of your rendering. You're looking at about a 1 in 10 to the 20th chance that it will even hit your scene, much less be reflected in the correct direction to hit your eyeball. The only reason why this works in reality is because the sun emits about 10 to the 45 photons per second. That's clearly not something that can be simulated. Assuming Moore's law continues, you might have a processor that can do that sometime in the next 1,000 years, but it's not something that we can feasibly simulate. So there are some ways that we can reduce this problem. One way is that you can sort of treat the sun as a plain light source. We can say, hey, the sun is so far away that basically we can assume that all the rays are coming in parallel, and we can just kind of make a plane above our scene, and the rays can shoot out of the plane. That way we'll guarantee that we can reduce down to only the rays that will hit our scene. And that reduces it significantly, but it's still a huge amount of waste. Another source of waste is that if you just shoot off a random photon and bounce it, the chances that it actually hits the eye is pretty tiny. It might bounce off in the wrong direction. It might run into some other object. So here's an example of that. So the one on the left hits, but the angle bounces it back off into the sky, never comes close to the guy's eyeball. The one on the right, it bounces off the cow, but the cactus is in the way, so you can't actually see it. This can be mitigated a bit by what I would call targeting, where we know that when photons hit a particular object, they tend to bounce off in the same direction that they came in, well, reflected across the normal, that is. But they don't all bounce off in that direction, and so you can kind of choose your rays to bounce off towards the eyeball and do some math to account for the statistics of that. But even that still has its limitations. You still end up with a lot of wasted rays. So the question is there a better way? There is, and the better solution is what we would call camera-to-light ray tracing. So what I was just describing, we simulate the rays by photons leaving the sun and eventually ending up in the camera. But like most things in physics, photons work basically the same direction if you trace them backwards. So we can start at the photons that hit the eyeball and then trace them backwards to the light source. And this helps reduce a lot of the waste. So we get better precision out of it because you can perfectly align every single ray to a pixel. You can just say, we'll just only consider the rays that hit center of pixel. Because you do this, we can make sure that every single primary ray, so a bit of terminology, primary rays are the ray that immediately gets emitted, and then when you reflect it, that's called a secondary ray. Reflected again, you can call it a tertiary ray, etc. So all of the primary rays, the ones leaving the camera, are necessary because every single one of them is a pixel. So there's no wasted primary rays. That's great. If we just emit rays out of the sun, there's a lot of waste, but if we emit them from the camera, there's no waste. We know that every primary ray will either hit an object or it will go off into the background, and both of those are useful. So if it hits an object, then that means that you have something there and you want to try and find a light source. If it goes to the background, then you want your skybox or something. We still have wasted rays, though, because you can still have misses that aren't useful. If you, for instance, fire off a ray towards the cactus and it's going to bounce off in some direction, that direction might not be towards the sun. But we can use sort of that same targeting technique to get so that our rays are far more likely to hit light sources. So basically, you fire the ray, and then when it hits the object, when you go to fire your secondary rays, you intentionally look for light sources and try to target them towards the light sources. And this helps reduce a lot of the waste. But it's still wasteful compared to, say, forward rendering. So I made the claim earlier that all 3D rendering is basically a simulation of light. So how does forward rendering fit into this? One way you can think about forward rendering is that forward rendering is just ray tracing, only it's from the perspective of the cactus rather than the perspective of the cowboy or the sun. So what do I mean by this? You can think of the geometry pipeline as firing rays towards the eyeball. So we take all the geometry in the scene and we project it into the space of the camera, and you can think of that as sort of that plus rasterization as sort of firing rays towards the eyeball and figuring out what rays go from the geometry to the eyeball. And then you can consider your fragment shader as firing rays towards your light sources, where it does some calculation where it walks to the light sources and computes lighting. You can consider that as sort of firing rays towards the sun. And so in that sense, it still is ray tracing. It's just that you're not starting from your camera or your light source. You're actually doing it from the perspective of the object. It might not be the best analogy, but there it is. So there is a bit of so there are some disadvantages to ray tracing. And there's a very good reason why we've been doing forward rendering for the past 20, 30 years. Longer than that even. One of the problems is that geometry intersection from arbitrary origin points is quite expensive, typically. In forward rendering, we're able to solve this by only worrying about geometry intersection from the perspective of the camera. So we smash all of the geometry with matrices into the camera frustum, and that's the only kind of intersection that we have to do. But in ray tracing, you have to start from an arbitrary point like a light source or an eyeball or a reflection point, and then figure out what that ray is going to hit in your scene. It also tends to be noisy. Most of the interesting ray tracing techniques involve multiple secondary rays and are a little bit kind of statistical in nature. And this tends to result in a pretty noisy output. So if you look at, say, Blender's cycles renderer, which is a ray tracer, and you watch it render something, when you first hit the render button, it starts out looking like complete garbage. And then over time, as it traces more and more and more rays, eventually you get to a pixel that's crystal clear. But it takes a while to get there. And so in order to do real-time ray tracing, of course, you can't have an infinite number of rays. You can't sit there and render for an hour. So you have to deal with that noise. And the way that it's typically done is with some sort of a post-processing denoise filter. So it adds a bit of extra step. So you, for one thing, have to do a bunch of rays in order to get something clean, and then you're not going to get something clean enough in real time, so you have to do this post-processing step. So that adds some extra work. Another disadvantage to it is that it tends to have worse memory access patterns for vertex data. Forward rendering, everything is set up for a very optimized streaming pipeline. But with ray tracing, you have to do lots of fetching based off of which objects you hit later. And the memory access patterns are pretty garbage. But there's some things that are a lot easier. So one thing that's pretty obvious is shadows. In forward rendering, typically this requires one depth pass per light, and then composite it all together at the end. But with ray tracing, you just fire a secondary ray and ask the question, does it hit anything on its way to the light source? If it does, you're in shadow. If it doesn't, you're good. It just kind of naturally falls out. Another is global illumination. This is what happens when light reflects off of one object and onto another and then back. So for instance, if you set a very, very blue object next to a piece of paper, you will see that the piece of paper starts to have a blue hint. And in order to get realistic looking lighting, you really have to come up with some way to emulate this. It's something it's one of those things that makes the difference between a scene that looks like it's 3D rendered and one that looks like it might actually be real. There are ways to fake this. One is called screen space ambient occlusion. It's fairly popular, but it requires multiple post-processing passes. And so that's additional work you have to do on the GPU. With ray tracing, it just kind of falls out because you can reflect a second time and see if it hits an object and then reflect off that object to get to your light source. And you can get this global illumination effect. It requires more levels of ray reflection, but it kind of naturally falls out. The other classic example is reflections. There are ways to try and fake it, but they're all garbage. The only way to get correct reflections is ray tracing, because reflections require a secondary ray, and the ways that you tend to fake them are with things like environment maps. And even when those are generated on the fly, because of limitations of forward rendering, the environment maps are always generated from one particular location, and then when you take that location and you try to apply it to all of the points that have reflections, if you're just looking for some like super shiny objects in your scene, it can be okay. But if you have lots of shiny objects and they're interacting with each other, it looks really bad. So that's another example. So ray tracing is useful. It's actually been used in games for a while now, at least limited amounts. Ray tracing in games did not start with DXR, but it's typically been fairly expensive, and part of the objective of DXR-like APIs is to make it more natural and more efficient. Okay, so you've now had my 15-minute primer to ray tracing, so let's talk about how this works in Vulkan. So there's two primary pieces. First piece is acceleration structures. These hold all of the geometry for your scene, and this is what allows for moderately efficient arbitrary ray geometry intersections. Again, they're still more expensive than just smashing all your geometry into camera space, but it makes it at least somewhat practical. The second part is the shader bit. For that, we add 6 new shader stages. Yes, that is correct. And this handles all of the ray dispatch, misses, hits, procedural geometry, and all of that jazz. Ray tracing, the Kronos Vulkan ray tracing API is basically a whole new 3D rendering API. There's very little overlap with the old rendering. It acts as a new pipeline bind point, and it is basically a completely separate thing like compute. Okay, so let's start with acceleration structures. An acceleration structure, as I said, is what holds your geometry. From the Vulkan API perspective, it is a memory-backed object similar to an image or a buffer. And it contains all of the geometry for an entire scene. So unlike forward rendering where you stream piles and piles of vertex data, in ray tracing, you have to dump all of your data for the entire scene into a single acceleration structure in order to be able to effectively ray trace. In order to do this, you have this acceleration structure object, and then you run this build pass. And there are commands to do it from the GPU. There's also indirect commands so that you can do a variable amount of geometry. And then there's also some CPU build commands. And typically the build is moderately expensive in the sense of you don't want to do it more than once per frame. Depending on how much geometry you have, once per frame might get tricky, but more on that in a bit. And then these are treated basically like any other object in Vulkan. So they're bound to descriptor sets, and then you pass it into the trace ray call in the shader. Vulkan is very careful to not specify how these work on the inside. There are several different potential implementations of an acceleration structure, but Vulkan just calls it a generic acceleration structure. There are 2 types of acceleration structures. There are top level and bottom level. Bottom level acceleration structures contain the actual geometry, like a bunch of triangles, for instance. And then the top level acceleration structures contain bottom level acceleration structures with a transform matrix. So this, because builds are expensive, this allows you to not have to rebuild all of your geometry every single time. You can build stuff into bottom level acceleration structures, and then all you have to rebuild as objects move around in your scene is the mutable objects like cloth, and then the top level acceleration structure, which contains everything. And this allows us to cut down the build time significantly. Geometry comes in 2 types: triangles and axis-aligned bounding boxes. Triangles are what you think they are. Axis-aligned bounding boxes are also pretty self-explanatory. It's a 3D box which is guaranteed to be axis aligned. It's not 6 arbitrary points. It's specified as 2 corners. Bottom level acceleration structures have a 2-level hierarchy of geometry data. So I said that bottom level acceleration structures contain the actual geometry data, and they actually have a hierarchy within them, where you have an array of geometries that's indexed in the shader by GL geometry index, and then each one of those geometries has an array of primitives. And the idea here is that you might have a bottom level acceleration structure that contains multiple sort of 3D objects in your world with different materials, and so you would separate those, each sort of single material, the thing that you would have as a single draw call in GL, would be a single geometry object in your acceleration structure. And then each one of those geometry objects can have multiple primitives. One important thing to note about acceleration structures is that they only contain position data. All of the other geometry input data like texture coordinates, colors, all of that jazz that usually gets passed as vertex attributes, that has to be fetched from the shader based off of GL geometry index and GL primitive ID. I mentioned before that ray tracing tends to have worse memory access patterns, and this is part of why. There's no ability to do any sort of fixed function vertex fetching and make that all streamlined. It's all fetched by the shader based off these indices. So one possible implementation, just to kind of give you an idea of how this might work, this is not the required implementation. This is one possible way to implement an acceleration structure. It's what's used by Intel Embry, which is a CPU-based ray tracer. If you want to sort of look at some things, it's all open source. One possible implementation is a BVH. BVH stands for Bounding Volume Hierarchy. And what that is it's an n-array tree data structure where the leaves are primitives, and each node in the tree knows its bounding volume. And so the tree is sorted into try and make the bounding volumes as small as possible, as quick as possible. And then these bounding volumes can be used to quickly discard geometry as you trace it through the scene. So let's give a concrete example of this. We have my scene again. If we were to make this into a BVH, the BVH might look something like this. So the root level contains the entire scene, and then first level of the tree splits things into objects, second level of the tree splits those objects down even further, etc. One can imagine that there are 3 or 4 more levels of the tree here, but that would get to be a lot of boxes on my slide and it wouldn't make any sense. So when we go to trace array, let's say we're going to trace array from the cowboy to the cactus, we can look at the bounding boxes and very quickly throw away most of our geometry. And so now when I go to do my ray geometry intersections, I don't have to look at the cow. I don't have to look at anything but the cowboy's head. And I can avoid a huge number of those potential ray triangle intersections. So the way that we accelerate it in forward rendering is we take all the geometry and smash it into vertex space. But we know that's useful because we want to test all of the geometry against that one origin. But with the ray tracing, we want to test geometry against arbitrary origins. So the objective is just to get rid of as much geometry as possible. And then once I've done that, eventually I have to take actual triangles, transform them from the perspective of the ray, and then do an intersection test. But the BVH allows you to throw away most of the geometry most of the time and substantially accelerate that process. So that's roughly how a BVH works. And that is one way, again, Vulkan doesn't specify, but that is one way that you can do an acceleration structure. Okay, let's talk about shaders. This is where things get fun. So I said that ray tracing adds 6 new shader stages. Let's talk about them. There are ray generation shaders. This is sort of the first step. This is what gets invoked by the VKCMD trace rays call. There are any hit shaders that get invoked anytime a primitive is detected. There are closest hit shaders, which get invoked after you've finished your ray traversal, and the closest hit gets invoked for whichever hit was closest to the eyeball, or the ray origin. There are miss shaders, which get invoked if ray traversal completes, but there were no hits. There are intersection shaders, and these are used to do procedural geometry. We'll talk more about that in a bit. And there are callable shaders, which can be invoked from anything to do basically anything you want. They're a pretty generic mechanism. Let's start with ray generation shaders. So ray generation shaders are the root of our call tree. And they are invoked directly by VKCMD trace rays. They look quite a bit like a compute shader on the surface. The biggest differences are that there is only one level of a 3D dispatch grid. There's none of this local global business. You just have a launch size. And there's no shared memory or barriers. And then like a compute shader, you really only get 2 inputs. You get the launch size and you get the launch ID. That's it. Everything else is done by fetching memory from SSBOs or UBOs or whatever you want based off those indices. Typically, you call VK trace rays EXT to fire primary rays from the ray generation shader. So there are no actual rays that happen by default. you have to explicitly fire them with traceways. I expect that as ray tracing gets more broadly accepted, we will see a lot of uses of the ray tracing pipelines that don't actually trace any rays, because the callable shaders allow for some potentially interesting tricks. But in the context of ray tracing, the primary purpose is to trace some rays. And you might trace more than one ray. But you can think of this as kind of, the dispatch as kind of being your camera. So that's where everything starts. From there, you trace some rays. And let's say we trace a ray, what happens? So the first thing that potentially happens is there might be some any hit shaders that get invoked. So any hit shaders get invoked for each hit. The ordering of the invocations along the way is not guaranteed. So because of the way the BVH or other acceleration structure traversal might work, there's no guarantee that you always get them in increasing or decreasing T order or anything like that. Inside of that shader, you get a bunch of information about the primitive. So there are 19 different built-in values. They include things like your launch ID and your launch size. So those are just sort of generic for every ray tracing stage. You also have things about the geometry, like you get the geometry index and the primitive ID. You also get information about the hit itself, like the hit TEXT tells you the distance from the ray origin to where that hit occurred. And there's a bunch of other stuff. Like I said, there's 19 built-ins. And then from this shader, you can modify ray traversal in two different ways. One is you can call ignore intersection, which tells it to ignore this hit and pretend that it's a miss. This is used for a similar reason as discard in a fragment shader. So let's say you have a tree and you have leaves, and those leaves have a texture that tells you what bits of the leaf actually exist. Normally in a forward rendering scenario, you would texture from that, and then if the alpha value is below some threshold, you would discard. Well, in ray tracing, you would texture, if the alpha value is below some threshold, you would ignore the intersection. So it's fairly similar to that. There's also terminate ray, which says, I'm absolutely sure that this is the hit that I want. Go ahead and kill the whole ray trace and just finish right now. So terminate ray does accept the hit, and then it immediately jumps to the closest hit shader and does not continue doing any additional hit checks or any hit shaders. The next one is closest hit. So the closest hit shader, like I said, gets invoked once all of the traversal has been completed, and it gets invoked only for the closest hit. It has exactly the same built-ins as any hit shaders. The difference is that the hit that you get in the closest shader is the one with the lowest T value. Typically, this is where most of your sort of fragment work would be done. You don't want to do all of your texturing and lighting on every single hit. You only want to do it on the closest one, typically. If you have, say, transparent geometry, like you have a glass or something, it's possible that you might want to do some of your fragment work in the any hit shader, but for solid geometry, you're most likely going to do it in the closest hit shader. One thing that you will notice in all of this is that there is no frame buffer. So I haven't talked about any sort of bindings. I said that when you fire off the RayGen shader, that it only has these launch IDs, and that's all anything basically has. So if you get done with your closest hit shader, you do your fragment work, and typically that's going to result in some sort of an image write using image load store. Instead of passing that data back up to the RayGen shader, you just write it from the closest hit shader usually. Miss shaders. So these happen when it gets to the end of ray traversal and no hits were accepted. That doesn't mean that there weren't any hits reported. It just means that for every hit that was reported, the any hit shader ignored the intersection. So if there were no hits accepted, then you get a miss shader. This is typically used for things like rendering the skybox. And it has basically the same built-ins, but the built-ins aren't, but it doesn't have any hit information. So all the hit built-ins are missing because, again, there was no hit. So, but it still has the ray built-ins. It still has the launch ID built-ins. Okay, intersection shaders. So these get kind of interesting. Intersection shaders are used for procedural geometry. So this is where your geometry isn't made up of triangles. It's instead something that you want to compute in a shader. Intersection shaders are always paired with the axis-aligned bounding box geometry. When an axis-aligned bounding box hit occurs, it fires an intersection shader. And instead of simply acting like any hit shader and doing a ignore intersection, the intersection shader has a lot more power. It doesn't have any of the sort of hit built-ins. All it knows is the minimum ray value or the maximum ray value that has been seen prior to that point. And instead, it computes the geometry, it takes the ray information, tries to figure out where that ray might intersect this shader computed geometry, and reports that hit via the report intersection intrinsic. That then causes an any hit shader to be invoked, and the any hit shader may then ignore that intersection. So it's possible that you could report one from the intersection shader and then get it ignored in an any hit shader. If the intersection shader does not explicitly report any intersections, it's considered a miss. So you might have, say, a perfect sphere that you want to do with your intersection shader, and you have a bounding box around that, and you shoot away, it hits the corner of the bounding box, but it doesn't actually hit the sphere. You would just not report any intersections. And then it would be considered a miss. Last shader stage is callable shaders. Callable shaders are invoked manually with the execute callable command. They can be invoked from any ray tracing shader stage. You can invoke them recursively, and they only have the 2 launch built-ins. And they can basically be used for whatever. I think we're likely to see eventually that there's going to be quite a bit of interesting sort of compute work that's done with callable shaders. Okay, so that's a rundown of the shader stages. If you're not lost, we're about to fix that. So let's give you 2 seconds to breathe, and then here we go. Ray tracing call stack. So ray tracing involves a call stack, and it is a real call stack. It is not like the sort of fake stuff that we usually do with inlining all the functions and shaders. Any ray tracing shader can call traceray or execute callable. There are implementation provided limits as to how deeply you can recurse, but in general, you're at least allowed to recurse to some extent. Intersection shaders can also invoke any hit shaders via report intersection. So that's another place where you can end up with a stack increase. And then there is ways that you pass data up and down this stack. So each time you call traceray, you provide it with a ray payload variable. And then this shows up in the called shader as ray payload in. So you would specify ray payload in your raygen shader, for instance, and then in your any hit shader, you could read the ray payload in variable and get some data out of it. All of the payloads are read-write, so you can also pass data back up the call stack by writing it into that variable and then reading it out after the traceray returns. And then for execute callable, it's basically the same thing. It's just called callable data. And yes, it is real stack. Yes, recursion is allowed. How do these shader calls work in hardware? We'll deal with that later, or never. Okay, so let's see if we can completely confuse you. One more bit. Shader binding tables. So we've got these call stacks. We've got this giant system of shaders that you can call from other shaders. But I still haven't talked about how we deal with the problem of sort of switching pipelines. So in forward rendering, it's fairly common for you to go along, do a draw call, switch pipelines, do another draw call, switch pipelines, do another draw call. And you need to do this in order to get different materials. So you might need different fragment shaders to have reflections, or to have shiny things, or to have matte things, or to have textures or not textures, etc. So how does this work with ray tracing? In ray tracing, it works by, when you build a ray tracing pipeline, you can have arbitrarily many shaders of each of the different stages. So instead of being restricted to one vertex shader, one fragment shader, and then 0 or 1 geometry and tessellation, each of the tessellation shaders, you're allowed as many raygen shaders and as many any hit and closest hit shaders as you want. When you compile the pipeline exports these as groups of shaders. So you can have there's different group types. You can have a single way generation shader. You can have an any hit closest hit pair for triangles. You can have an intersection any hit closest hit tuple for axis-bound binding boxes, or you can have a single callable shader. These are the sort of groups. And you can think of groups as kind of mini pipelines within the bigger pipeline. And then you have these shader binding tables. So each shader group, when you get it from the pipeline, you get a 32-bit handle. The handle contains all of the information required to dispatch those shaders. So if we were theoretically going to do this on Intel, the handle would contain things like the instruction pointer and the SIMD width and all of that information that we would usually pass along to the hardware. And then the client takes those handles and they put them in a buffer for us. We do not get to control whether this buffer is in memory. We do not get to control which handles they put there. The only requirement is that they have to use the bound pipeline. So they put those handles in a buffer. They call those buffers a table, and they hand those tables to the traceways call. So here is the traceways call. It contains 4 tables. It contains a RageEng shader binding table, a miss binding table, a hit binding table, and a callable binding table. And then we pull those shaders out of the binding tables and execute them. The rate generation shader is always the first one in the binding table. Okay, that's pretty easy. It sits at the root of the call tree. For miss shaders, when you do a traceway, you pass the binding table index for the miss shader. You only have one for the traceway because it's what happens when it misses. Makes sense. For hit and intersection shaders, the index is calculated based off of the geometry index that you placed into the acceleration structure, and some other bits of data that come in from the traceway call and the the traceway call at the API side and the traceway call in the shader. But the important thing is that the geometry index is in there. And so that's why we have, if you remember from 15 minutes ago when I was talking about acceleration structures, that's why acceleration structures are broken into geometries that contain primitives. Because that geometry index is used to calculate which hit shaders to use. And this is what allows you to get your different materials. So you make it so that each one of your different materials is a unique geometry, and then you place the hit shaders required to handle those materials into the right place in the buffer for that geometry index. And that's what allows for the sort of shader switching that we normally get with multiple draw calls. And then for callable shaders, execute callable takes an SBT index. And that's it. Simple, right? At this point, I will congratulate you if you are still awake and your brain still works, and I will take questions.
Okay, so we have a couple of questions. First one is quoting. I hope we can get a mention of the optional array query support, because that's a fun feature.
I do not know offhand what all is public about that, and that's why I did not put any of it in my slides. I don't believe that we have a cross-vendor array query extension that has been released yet. I think I can reasonably say that it is on Khronos's radar and that we will be doing stuff with it. But I didn't want to talk about any of those details because, again, there's no Khronos published public spec for that yet.
Okay.
You can go look at the DXR docs, and anything that Khronos does is not going to be too different from that, but we haven't published anything yet.
Okay, another question is, can a callable shader return something to the other shader that called it?
Yes, so that's where the callable data payloads come in. You can pass data up and down the stack by using the callable data. It works the same as rate queries. I had that in a couple slides. So it's the same as with the traceway. You provide a payload in terms of a callable data variable, and then in the callable shader, it shows up as callable data in. And it's the same thing. It's read-write from both sides. So you can pass data both up and down the stack.
Okay, another question. Are the bounding volumes actually boxes or shapes or ellipses? So for the geometry that gets specified,
the axis line bounding boxes are boxes, and they are guaranteed to be aligned to the axes relative to the transformation matrix. In terms of how it's actually stored in the acceleration structure, you can do whatever you want. Vulkan does not specify. You could have spheres if you think that that's a good bounding mechanism. You can use ellipses. You can use dodecahedrons. It's up to you. I think boxes are fairly common just because it's really efficient to compute ray box intersections, but you can do whatever you want.
Okay, one more question. Are callable shaders called with the same invocation, or does it issue a new shader?
Unspecified. So there is one sort of hint in the spec about how this might work, and that is that trace rays, report intersection, and execute callable all mess up your built-ins. So it is possible that it ends up invoking a whole new shader. And it's actually possible that when you get the return from the execute callable trace ray or report intersection, that you don't end up in the same shader that you had originally. So we allow for some interesting things where, from a spec perspective, what it looks like is you call off to the execute callable, and when you come back, you might end up with different neighbors. So you might end up, if you do subgroup operations afterwards, you might find that the shaders that were in your subgroup before the execute callable are not the same shaders that are in your subgroup after the execute callable. And this is to allow for things like ending the current shader, spawning a whole new shader to do the callable, and then that spawns a third shader on the return, which is not actually the same shader as you started with. Precisely to deal with the obvious issue that call stacks are really painful to do in parallel. So how is it actually implemented? It doesn't say, but the spec does explicitly allow for all sorts of cases where you may end up invoking whole new shaders.
So you have mentioned having several different mini pipelines. Are those generally efficient on the hardware?
They'd better be. If you're going to be able to trace rays at millions and millions of rays per second, which is, I don't remember how many million rays per second the recent NVIDIA cards can do. Somebody can probably provide that information in IRC. You need to be able to invoke them very efficiently. So they had better be. But I can't say how efficient they are on any particular piece of hardware in any concrete terms.
Okay, can you merge some or even all of those shader stages into a single big one and then just jump within that?
Potentially. So let's see if I can find the slide. So as I said, groups there's kind of these defined types of groups. So you have ray generation shader, and then for triangle geometry, any hit and your closest hit shader are guaranteed to come together. So if you wanted to, you could potentially do some sort of cross-stage optimization across that. For intersection, procedural geometry, you have your intersection, your any hit, and your closest hit all together. So again, you could theoretically do some cross-stage optimization with that. In fact, one thing you can do is you can actually, because the only way an any hit shader gets called from an intersection shader is if it calls reported intersection, you can actually inline the any hit shader into the intersection shader if you wanted to. So there's definitely some opportunities there. It is also theoretically possible to implement it as one big giant compute shader. It would be a big compile time because you would have to compile everything together, but it could be done. So there's any such grouping would, of course, end up with giant switch statements because shader binding tables allow for all of this arbitrary switching out of shader stages, but it could, in theory, be done. So there's options there. For the most part, though, they probably are going to end up as separate shaders. But I can't talk about details of anybody's implementations. But in theory, they act like separate shaders, but they can be combined depending on what the hardware likes to do. and depending on how big a switch statements you want to have.
So is the array/callable payload ext stuff fixed, or can apps put arbitrary stuff in there, kind of like linking VSPS pipelines?
They can put arbitrary stuff in there. There are some, I believe, limits as to how big they're allowed to be, but by and large, you can put whatever in there you want. There is another one that I didn't mention, which is for transmitting data between the intersection and the any hit shader, called the hit attributes. That one is a little bit more fixed. It's still arbitrary, but there is a limit on it. And when you have triangle geometry, it's fixed to be a single vec3 that contains the barycentric coordinates for the hit. But the callable data and the array payload are completely arbitrary up to some hardware-defined limit, or some implementation-defined limit.
Okay, Arcady, you've got... sorry, no. The stage. I'm sorry. Go ahead.
All right. Hi, this is Easy GL and Vulkan tests with Shader Runner and Ember. I am Arcady Goldmints-Orlov. I work for Igalia on Mesa development, so making graphics drivers work. And why is this interesting? Well, to make graphics drivers work, you have to test them. We have wonderful test suites. We have Piglet, we have the Chronos conformance test suite, but they're big and complicated, and they're full of C code or C++. But inside that, those tools, there are some neat little scripting tools. There's Shader Runner in Piglet, and there's Ember included in the CTS. And they're quite useful both for developing new tests, so you can get a test going a lot quicker, and for debugging code, writing a quick little test to see what is it doing wrong and try to kind of narrow down the test case, for example. So yeah, programming is hard. Let's go scripting. So rather than write a whole program, in C or C++ to deal with, all the basic stuff that it takes to get going with OpenGL or with Vulkan, which is even more work. You can just use these scripting languages. They take care of all the hard stuff for you. It's very convenient if you want to, for example, just run a shader. You can do that quite easily. So for OpenGL tests, Shader Runner is part of Piglet. For scripting Vulkan, Ember is used in the Vulkan CTS, but it's actually a separate project, and you can run it by itself outside the CTS. So where do you find Shader Runner? When you build Piglet, it can be found in bin/shader runner. You run it just like that. You give it the name of the test script that you want it to run. And by default, it actually draws into a window and keeps that window up on your screen so you can see the result of your test and maybe visually inspect what's going on if it's doing something wrong. But it also has a mode to run automatically and just print the pass or fail result and not keep the window up on your screen. And it has a mode to draw off screen, so you don't have windows popping up on your screen. For whatever reason, you have to pass those options at the end after the name of the shader test that you want to run. But those are handy options. So here's an example of a Shader Runner shader test file. It starts with a require section where you just tell it what version of GL you need, what version of GLSL. You can also specify GLES. After that, you specify the shaders for if you have a vertex shader, you can specify that. If you don't care to do anything interesting in the vertex shader, you just say pass through, and it just passes through the coordinates and doesn't do anything interesting. Then you have your fragment shader, which is just you write some GLSL code. And it supports all the other usual shader stages as well. I don't think it does ray tracing yet. After that, you have your actual test script, which is a series of commands. So here it sets the clear color, does a clear, draws a rectangle, and then the probe command is what actually does sort of the testing part and checks the values that got drawn. In this case, it checks that all the pixels got this color. There are many, many other commands. Just as some examples, there's a compute command, so you can run a compute shader. It supports various types of buffer objects, SSBOs. You can create SSBOs. You can set data in SSBOs. You can probe them after you've run your shader to make sure the right things have been written. There are various different things that you can do with probe. You can probe rectangles that are, sub-rectangles of the frame buffer to make sure that those are right and do more complicated probes. Unfortunately, these commands are not particularly well documented, and the only real reference for these commands is actually the shader runner source code. There's a giant chain of if-else statements. That's the parser, and that's kind of the only place where you can find all of these commands. But there are also lots of shader test files that are included with Piglet that have all of these commands and examples of how to use them. So you can look at those for inspiration. And of course, you can always add your own commands if you can't find what you want. So for Vulkan scripting, there is Amber, which was created by Google and was kind of explicitly meant to be a shader runner-like thing, but for Vulkan. It has its own GitHub project, but it's also integrated into the Vulkan CTS. So it's actually, if you have the Vulkan CTS source code, you can find it in this external/Amber directory. And for its script files, it supports multiple syntaxes. It has its own Amber script syntax, and it also supports basically the same shader runner syntax, but for Vulkan. And there are examples of each included with the Amber source. So here's an example of the Amber script syntax. It's just a different syntax for kind of much the same idea. You have your shaders. You can also have a pass-through vertex shader if that's what you want. Then you have your fragment shader in GLSL. You can actually have your shader in a number of different formats. It can get compiled through GL-Slang validator, or you can have an actual just SPIR-V binary or assembly shader as well. Then after that, you have your buffers, in this case, just the frame buffer, but you could have other kinds of buffers. You could set contents in them. Then you declare one or more pipelines, which, then you tell it what shaders you want to go with that pipeline, what buffers you want to go with that pipeline. And finally, you run the pipeline. You tell it to draw a rectangle. You can tell it to draw other things. And the expect command is how you check the results. In this case, it's the same check that all the pixels in the frame buffer have this color. So more Ember script commands. You can have compute pipelines. As I mentioned earlier, you can specify initialization data for buffers. So you can, for example, you can fill it a buffer with zeros or ones or whatever value you want. There's even a command to fill a buffer with an incrementing value. And then with expect, you can also do a number of other things. This RMSE command is interesting because it computes the root mean square error between two buffers and checks that it's within the given tolerance. But there's lots and lots of commands, and they actually are documented. There is an actual documentation file that describes all of the commands in the source code in the doc directory. Other things about Amber, it supports Vulkan validation layers and actually tries to use them by default. You can disable them, though, if that's not what you want. One very useful feature of Amber is that you can dump any buffers after your script has run to a PNG file with these capital I and lowercase I options. It's very useful for debugging. You can actually dump any number of buffers. So for example, when you have multiple render targets, you just dump all of them. You have a bunch of PNG files. You can quickly check them to see what's going on. As I mentioned, shaders can be in SpearV, GL, or GLSL. The latter get compiled with GL-Slang validator, on which Amber actually depends. You can have multi-step tests. So a common thing that I've seen is, having two different pipelines drawing to two different buffers, and then maybe you can compare them with an expect command, or even have a third step with a third pipeline that actually compares the two buffers in a shader and then draws green for good and red for not good. So that's an interesting thing you can do. And I'm sure there are many examples included with the Amber source, as I mentioned, or in the Vulkan conformance test suite, and more tests are being written with Amber because it's easier. So in conclusion, I found these tools to be very useful for writing quick tests, especially, for example, when I'm working on the compiler. All I want to do is run the shader and see what it does. I don't really care about anything else. Sometimes maybe I just want to compile the shader, and this is a very quick way to do that. It's very useful for debugging. For example, I have a failing test in the CTS, and it has some complicated shader. I can slowly cut it down to see what part is actually going wrong, what's going on there, where to fix it. And hopefully, if you haven't heard about these tools already, hopefully you'll find them interesting and useful. And hopefully also we can make the magic of open source happen. And some of you may want to improve these tools, which would be great. And I guess that's it for me. Any questions?
So far, we do not have any questions, or we can wait a little bit.
So a question for kind of the audience in general. Are you aware of these tools? Have you used them before? Do you think they're useful?
That's going to be an interesting way of answering.
Curious, yeah.
Maybe you can use the XDC 2020 channel to just say yay, nay. Get a feel.
I feel like this isn't nearly as exciting as ray tracing.
So Liud was saying that he's been using Shader Runner. I guess anyway, it would be quite difficult for people to, for us to see. So I guess people are just self-censoring.
Yeah. Well, anyway, hopefully people will find this useful. Liud says, it helped me learn GL, which is definitely kind of a good way to get into GL, because you don't have to do all of the setup. It kind of takes care of a lot of things for you.
That is true. It was much easier if you want to set a pipeline. And very easy. And Samuel also has been. Okay, well, thanks a lot for the talk, Arcady. And the next talk is and the last talk is gonna be by AMD. Don't bake your graphic cards. So, talk to you. It's in 14 minutes. So, see you then. Bye.
Okay.
Folks, the stage is yours.
Sure, thank you. So, hello everyone. I welcome you all to this presentation. Good morning, good afternoon, good evening to all of you. And I have my colleague Alex Stryker with me for this presentation. My name is Rajneesh Bhardwaj, and I work for AMD as the Linux kernel engineer for ROCm team. ROCm is Radio on Open Compute Module, which is AMD's open source solution for HPC and compute graphics. So my focus area for my work is, kernel fusion driver, which is a subset of AMD GPU graphics driver. But I do have some background on Linux kernel and power management as well. So with that, let's start the presentation. So talking about this presentation, don't bake your graphics card. It sounds unusual, but I'm pretty sure that for this community, especially the graphics people, this must be something either that they have done in the past or must have definitely heard about it. So what is it? Is it fact? Is it mystery? Is it myth? What is it exactly about? So this whole thing of baking the GPUs is not new, and oftentimes people do bake their graphics card in their oven in their kitchen. And why do they do so? Because sometimes when the graphics chips or some of the older electronic components get older, especially talking about GPUs here, and they suddenly stop working, maybe because of the extra amount of stress that they have to deal with, overheating, excessive heating, vibrations due to fan, moisture content. So sometimes the PCB, doesn't work the way it's supposed to. And primarily, the reasons that I mentioned are the reasons. So what people think typically, and based on that belief, they really preheat the oven to 100 degrees, 200 degrees Celsius, put their graphics cards and feel that if there was some broken printed circuit, then the molten solder and the flux, when it again cools down and it evaporates the impurities, it will refix the problem. Especially the ball grid arrays, the GPUs that sit on the array. Sometimes it's because of the aging factors. So the loose ends are sometimes fixed and it works, but it's largely a myth, and it works only in 5% of the cases, and most of the times it doesn't. And the reason is that the graphics cards have a typical life cycle of 3 or 4 times of PCB reflow technologies. So if you have an old spare card which is not physically damaged, but was working and suddenly doesn't work, and you believe that it's because of moisture or things like this, you may consider baking it, given that you don't use that oven for cooking, because sometimes these products might contain lead. There can be toxic fumes, gases, which can contaminate, and of course, the heat distribution in the normal oven is not uniform. We need special ovens for PCB reflow technologies where the heat distribution is usually non-uniform. Some of the larger components, such as GPU, they tend to sink more heat, so they tend to be heated more, and the smaller components, if heated to the same degree, might actually get burnt. So it's a dangerous operation to do in your own oven, but if you want to do that, remember this disclaimer, it's an expert thing, and you must be very lucky, and don't otherwise try this thing at home. But this talk is actually not about baking, especially the graphics card. It's about similar sounding technologies called BOCO and BACO. And interestingly, these technologies help in keeping the graphics card cool, save power, so that you don't have to bake your graphics card, because it might end up longer, because now it's only used, the graphics card turns up only when it is really used. Otherwise, it remains in a silent mode and less power saving state. So this is basically the theme of this presentation. So with that, let's move ahead. But before we get into the details of BACO and BOCO, let's get rid of some bus and chip jargon. So B stands for bus, O for off, C for chip, and A for alive. So BOCO means bus off, chip off, and BACO means bus alive, chip off. And we are talking about the PCI bus here. So that's about this. And then further, let's delve into the specifics of BACO and BOCO. So BACO and BOCO, before we go into these technologies, I want to give a brief background about BOCO and BACO. So BOCO has been around for a while, and it was originally introduced with AMD's Power Express technology. And later it evolved. We had something like BACO, but the support for BACO in Linux was recently completed, although it has been existing in some patches for some other activities like GPU reset for a while. But for the runtime power management, it is recently made available as part of mainline Linux kernel. I want to talk briefly about the device power states because it essentially is about device GPU power states. So D0 is the device state where the device is fully operational and functional, and D1, D2, and D3 are the device low power states. These states have varying degree of power consumption, context saving with driver and firmware, varying degree of resume latencies, and different wake-up capabilities. PCI spec further defines two more substates of D3 state, which is the lowest possible power state of a device, called D3 hot and D3 cold. So think of D3 hot as a state where the power is not physically removed from the device, although it is turned off to a larger degree. On the other hand, D3 cold is actually like removing the power from the device, and it is essentially turned off. But in some cases, the device might still draw a very low amount of current for sideband access, but most of the times D3 cold means it is completely cold and turned off. There is no live wire connected to the device, basically. So BOCO basically powers down the GPU completely and offers more power savings. So BOCO is sort of, you can think of BOCO as D3 cold. And BACO, which has the main contrasting difference with BOCO is that the PCI bus is kept alive. The PCI configuration space is always available for the operating system to look at. So that's BACO for you. We'll look at the characteristics of BACO and BOCO in coming slides. Yeah. So as I mentioned, BOCO was introduced earlier, originally with AMD Power Express laptops, whereas BACO was, a low power solution for DGPU, especially targeted at hybrid and desktop segment. BOCO is mostly handled by ACP. It used to be handled by ACPI ATPX methods, and now the PR3 runtime power management methods. And ATPX methods and these methods are actually defined in the ACPI tables for the device as part of the system BIOS. BACO, on the other hand, is largely initiated by the device driver, and once the entry to the D3 hot state is triggered by the PCI device driver, then internal underlying SMU firmware takes care of handling all the low-level interactions, shutting down the clocks like SPLL, DPLL, etc. The bus interface obviously remains on in case of BACO, so the device is always discoverable. But in case of BOCO, it completely disappears from the device. Talking about the wake-up latency and power savings, so obviously BOCO saves more power for us, but at the cost of more resume latency. BACO, on the other hand, gives good amount of power savings, including the fan control. The fan completely turns off when the device is not in use, and it offers the better wake-up latencies for the resume operation compared to BOCO, because in this case of BACO, the bus interface is on, so the retraining of the PCI link is not needed. The only thing that is still required in case of BACO is the VRAM or the memory modules retraining, which is much more in case of BOCO, because BOCO has to deal with memory retraining as well as the PCI link reestablishment. Yeah, so this is about BACO and BOCO, and how do they converge into the larger picture is what we're going to talk about now. So I mentioned that BACO was originally meant to save power, but it was initially being used to have the GPU reset mechanisms in place, and later the support was extended when the things became more stabilized for runtime power management on Linux. But before we go into the specifics of runtime power management, I want to briefly also talk about the larger scheme of runtime, the Linux power management scheme. So broadly, we can classify the power management on Linux in two different or in two ways: the system-wide power management and component-wide power management. So system-wide power management is the framework where you really have a user input, or a user space has some say in initiating the suspend trigger at the system level, not just the device, but the whole system suspends. So there are two things here: suspend to RAM, also known as legacy ACPAS3, and the recent contemporary suspend to idle, which is an advanced power-saving technique in Linux kernel. Especially the advanced states like S0ix states are achieved through suspend to idle. On the other hand, talking about dynamic power management, there are various frameworks available for us in the Linux kernel, such as CPU frag, device frag, runtime power management, OPP, operating point performance, GenPD, clock framework, regulator framework, and so on. But for our case, we are interested in runtime power management because we are actually talking about the graphics power management here. So, so the most important, data structure here for power management in general is dev PMOps, and it provides some callback hooks which device driver is supposed to implement, and the runtime underscore suspend is basically the hook that is called from runtime underscore idle method, and this is completely device initiated and is autonomous. So there is no user input here. When there is inactivity on the device, it is the responsibility of the device driver to detect it and make sure that the runtime idle is called, and then eventually runtime suspend is called. And with that runtime suspend callbacks, the AMD GPU device suspend methods are triggered, which eventually lead to BECO or BOCO, depending on the ASIC and depending on the underlying hardware that supports it. So there are some helper functions here as well, especially to support and enable the proper working of the graphics driver. We should look at some important functions here for PM runtime. There are two variants here largely, get variants and put variants. So get variants are basically the variants which make sure that the devices do not runtime suspend until the reference count held by calling of these APIs is in place. And once the actual workload is done, let's say you're running a compute kernel or a graphics or an initiator, and if that thing completes, now you have nothing else to do. So in that case, it is the responsibility that a corresponding PM runtime put sync or put auto suspend is also supposedly called by the device driver. So the way these APIs work is basically on a simple concept of a reference counter. So when we want to do some meaningful work, we need to hold this sort of a reference count, achieve the work, and when the work is done, we have to release this. So there are various APIs, and this is what is used in making the BECO implementation for a runtime suspend framework. To support BECO, we had to deal with some other dependencies. Obviously, we are talking about device D3 states here. So graphics alone cannot be put into D3 if we have dependencies on display audio, especially the HDMI audio and all the codecs related to it. So they need to be runtime suspended also, without which the GPU cannot be put properly into runtime suspend methods. So there were some broken pieces here, especially with regards to the legacy, VGA switcheroo related problems. VGA switcheroo is basically Linux subsystem for hybrid laptops graphics, and it used to come in two different flavors, muxed and muxless. Basically, these are both are dual GPU systems with a multiplexer chip to switch the output between multiple GPUs. So you have integrated GPU as well as a discrete GPU, and with the mux method, you can have them both. But on a muxless setup, there are two GPUs, but only one of them is actually connected to the output at the time. So there were some refactoring required because of some legacy ATPX and power handling issues with that code, which was recently fixed in Linux kernel 5.6. So with that, the only pending piece to support Beko completely on Linux for runtime power management was the kernel fusion driver. So KFD, as I mentioned briefly earlier, is a part of AMD GPU driver. It used to exist as a separate entity earlier, but now it is a part of proper AMD GPU Linux driver. And it works together, but it doesn't have its own power management implementation. It relies largely on the initiated callbacks from AMD GPU. KFD driver is used for compute. Somebody had something to say? Okay. So the KFD driver is used for compute applications, supports runtime, supports user mode queues. And the way we worked around this was basically we looked at the bare minimal entity that we could consider as a valid workload. And what we found is that we use the per process device data, PDD, as part of any active queue. And for the whole life cycle of this PDD, until this PDD is destroyed, we hold the runtime PM lock, and we release it only when the PDD is completely destroyed. So this change also landed in the Linux kernel, I think, earlier this year. And with that, it basically laid the foundation of completing all the missing pieces to enable Beko completely. So right now, if you boot the kernel with run PM enabled, which is the default setting also as a module param, you will see this Beko already kicking in. So I think you should be aware of the fact that if you see the GPU going idle after 5 seconds or so, it is because of the fact that Beko has kicked in, and we have programmed 5 seconds as the default auto suspend timeout for Beko trigger for runtime suspend. I want to also briefly mention about the GPU reset techniques here, because Beko is also used for resetting the GPU. The module param AMD GPU reset method can take various inputs. Basically, it tells us which mode we would like the GPU to be reset with. Mode 0 is a legacy mode, is not used, but what largely is used on the contemporary chips like Navi and Vega is mode 1. It has its own limitations. Then we have something called mode 2, which is mostly used for the APUs, because mode 2 is lesser reset than compared to mode 1. And in mode 1, we reset most of the IPs. In mode 2, we don't reset, it's a limited reset. Like we basically don't reset graphics and multimedia. So especially, the access to VRAM, the system memory on APUs is a contention. So we cannot use mode 1 on those things, on those chips. So we use mode 2 for that. And Beko is ultimately used where everything else apparently fails, especially in case of ECC and RAS errors, because when we use mode 1 for resetting, it takes ultimately the path is through PSP to SMU, but it also relies on access to the MM hub. And if there is a problem with MM hub access itself, then maybe because of the sync flood or whatever reason, the response to the driver might be forever delayed, and it might not really serve the purpose. So for that purpose, we can use Beko to trigger a reset, especially for RAS and ECC scenarios. There is a debug FS interface also available called AMD GPU recover. If you read this file, if you do a cat on this file, it can also manually trigger a GPU reset, and it internally checks whether the underlying chip is supporting Beko. And on the next fence and wait, it basically implements the same GPU reset mechanism. So current cut stream status, it's fully available upstream. Don't boot your kernel with run PM disabled. And if your graphics card, if your AMD graphics card is supporting Beko, it will be automatically enabled. So if there is no active workload, the graphics device should ideally suspend within 5 seconds. You should see fan spinning down and eventually coming to a complete halt. And if you are using the graphics card for compute, the same behavior will be observed. So I've also listed down the important APIs that one might look at if somebody wants to understand internals of Bako, the SMU interactions, how is it basically set up by the device driver, and how the entry and exit sequencing is performed. The main algorithm for Bako entry and exit is implemented inside the firmware, but the responsibility of the driver is basically what these APIs cater to. So with that, I think I have come to an end, and I would like to end this presentation now with a note of thanks to my colleague Alex Deucher and Felix QLA for their support. So thank you. Open for questions now.
Okay, thank you very much for your presentation. Seems like the chat is very hungry because they are talking all about bacon and baking. There's also one question. So what is the absolute amount of power used by the entire device in Bako state? Also, how does it compare to the state before the Bako was implemented?
So it's very subjective to talk about the absolute power, but think of it, if suppose there is no runtime PM implemented, and the GPU is always kept alive, especially for compute. So for compute, we never had this working, even if the kernel supported it. But for compute, we used to boot the kernel with run PM disabled, and our GPUs were, always burning the power to the full throttle. And whatever power management was implemented in the firmware. There was no real power management happening from the kernel or driver side. So with that, I think right now the scenario is if you have a compute kernel to run, then only the GPU will be woken up. If the device is already suspended, it will be woken up. The lock will be held. When the workload is done, the lock will be released and the GPU will suspend again. So compare it with, fully working state of a GPU, which is, we are talking about watts here, not milliwatts. Versus where it's suspended, we are talking about a few milliwatts.
Yeah, so I mean, like in the case of like Bako, for example, if you have an idle GPU that's still powered up, depending on the GPU, you're looking at anywhere from like 5 to 7 watts generally, on a desktop card, and then substantially less than that, like a few milliwatts once it's in Bako state, and no power at all in the Bako state.
Okay.
I don't know the exact measurements offhand, but something like that.
Okay, thank you very much. That's it for the questions, and you were the last presentation of the day, so we're closing for today. Thank you.
All right, thanks.